Imagine something so massive that even light can't escape its grip. Something invisible yet powerful enough to tear apart stars. Today, we're diving into the universe's darkest secret, black holes. And trust me, what you're about to discover will change how you see space forever. Black holes aren't just sci-fi monsters. They're real. They're lurking in every corner of our galaxy, hiding in plain sight. But how do we study something we can't even see? And why should you care about these cosmic giants? Stick around, because we're about to unravel the mystery together. Here's the problem. Black holes are invisible. They don't reflect light. They don't emit heat. Nothing escapes them. So how do scientists even know they exist? It's like trying to study a ghost. For decades, astronomers were stumped, chasing shadows and theories without proof. But then came a breakthrough that changed everything. Let's start with the basics. A black hole forms when a massive star dies. Not just any star. Think 20 times bigger than our sun. When it runs out of fuel, it collapses under its own weight. Imagine squeezing a mountain into a grain of sand. That's the density we're talking about. The gravity becomes so intense that it punches a hole in space itself. This hole is the black hole. Now, the edge of a black hole is called the event horizon. Cross this line, and you're gone forever. No turning back. But here's where it gets wild. Time slows down near a black hole. If you watched someone fall in, they'd appear frozen in time, fading slowly like a ghost. That's Einstein's theory of relativity in action. But how do we find them if they're invisible? Scientists look for clues. For example, when a black hole eats nearby gas or stars, it heats up and glows. We can't see the black hole, but we see the X-rays from its last meal. It's like spotting a shark by the blood in the water. Take Sagittarius, a star, the black hole at the center of our galaxy. It's 4 million times heavier than our sun, yet it fits inside Mercury's orbit. We only found it by tracking stars orbiting something invisible at insane speeds, like a cosmic game of hide and seek. And black holes aren't rare. There could be millions in our galaxy alone. Some are small, just a few miles wide. Others are supermassive, billions of times heavier than the sun. These giants sit at the heart of galaxies, shaping how stars form and how galaxies evolve. They're the architects of the universe. Now for the most shocking fact, black holes might not last forever. Stephen Hawking discovered they slowly leak energy, like a pot of boiling water. Over trillions of years, they evaporate into nothing. Poof, gone. But here's the twist. When a black hole dies, it could release everything it ever swallowed. Stars, planets, even information. It's like the universe's ultimate recycling bin. So, black holes are invisible giants that bend time, devour stars, and build galaxies. They're not just empty voids. They're dynamic, powerful, and full of surprises. We've learned to spot them by their effects, and we're just beginning to understand their secrets. Imagine standing on the edge of something so powerful, it warps the very fabric of reality. A place where time slows to a crawl, gravity becomes infinite, and even light itself gets trapped forever. Today, we're diving into the universe's most terrifying and fascinating creation, black holes. These invisible giants are hiding in plain sight, bending the rules of physics and swallowing entire stars. By the time we finish, you'll understand why scientists call them the ultimate cosmic mystery, and why they might hold the key to everything. Black holes aren't just some sci-fi fantasy. They're real, they're everywhere, and they're reshaping our understanding of space. For centuries, they existed only in equations and theories. Now, thanks to cutting-edge technology, we're finally uncovering their secrets. But here's the thing. The more we learn, the stranger they get. From their birth in dying stars to their role as galactic architects, black holes challenge everything we thought we knew about the universe. And trust me, what you're about to hear will make you question reality itself. Here's the mind-boggling problem. Black holes are invisible. They don't reflect light. They don't emit heat. And they don't make a sound. They're like cosmic ghosts, leaving no trace, no shadow, no evidence of their existence. For decades, astronomers were chasing shadows, relying on math and imagination to hunt something that might not even be real. How do you study an object that's literally undetectable? It's like trying to prove there's an elephant in the room when you can't see, hear, or touch it. Even Einstein, the genius who predicted them, doubted they'd ever be found. The challenge isn't just finding them, it's understanding how something so impossible could actually exist. Let's start with the basics. What exactly is a black hole? Picture a star, massive, brilliant, burning for billions of years. When that star runs out of fuel, it collapses under its own weight. Not just a little collapse. We're talking about a star 20 times bigger than our sun crushing itself into a space smaller than a city. The gravity becomes so intense that it punches a hole in space-time itself. That hole is the black hole. Now, the edge of a black hole is called the event horizon. It's not a solid surface. It's a boundary where escape becomes impossible. Cross that line, and you're gone forever. Not even light, the fastest thing in the universe, can climb out. That's why black holes look black. They're not empty. They're so dense that nothing escapes their pull. But here's where it gets wild. Near a black hole, time itself bends. If you watched someone fall toward one, they'd seem to slow down, frozen at the edge like a fading photograph. Meanwhile, for the person falling, time would feel normal, until they get stretched into spaghetti by the gravity. Scientists call this spaghettification. And yes, it's as terrifying as it sounds. The gravity pulls harder on your feet than your head, stretching you thinner and thinner until you're a stream of particles. So how do we find these invisible monsters? We look for their victims. When a black hole pulls in gas or dust from nearby stars, that material heats up and glows brightly in X-rays. We can't see the black hole, but we see the X-ray fireworks from its cosmic lunch. It's like spotting a tornado by the debris it scatters. Take Sagittarius, a star, the black hole at the center of our Milky Way galaxy. It's 4 million times heavier than our sun, yet it's smaller than Mercury's orbit. We only found it by watching stars whip around an invisible point at insane speeds, like watching marbles orbit a drain. Those stars move so fast, up to 15 million miles per hour, that only something incredibly massive could hold them in place. That something is Sagittarius, a star. But black holes aren't rare. Astronomers think there could be 100 million of them in our galaxy alone. Most are small, just a few miles wide. Others are supermassive, billions of times heavier than the sun. These giants sit at the heart of nearly every large galaxy, including ours. They're like cosmic engines, gobbling up material and spewing out energy that shapes how galaxies form and grow. Without them, the universe wouldn't look the way it does. Now, let's talk about how black holes form. It's not just about dying stars. Some might be born from the Big Bang itself, primordial black holes floating around since the dawn of time. Others grow by colliding and merging with each other. When two black holes crash, they send ripples through space called gravitational waves. We've detected these waves with supersensitive instruments, proving Einstein was right again. But here's the mind-bending part. Black holes might not be holes at all. They could be fuzzballs, tangled knots of quantum strings, or portals to other universes. Some theories even suggest they're holograms, projecting a 3D illusion from a 2D surface. It's like the universe is playing tricks on us. And get this, if you fell into a black hole, you might not die instantly. For a supermassive black hole, the event horizon is so far out that the gravity pull isn't deadly at first. You could float inside, watching the universe distort around you. Outside, time would fly by. Billions of years might pass in what feels like minutes to you. But eventually, you'd hit the singularity, the point where density becomes infinite and physics breaks down. No one knows what happens there. Maybe you'd be crushed. Maybe you'd enter another dimension. It's the ultimate mystery. Black holes also have a strange effect on their surroundings. They can create accretion disks, swirling clouds of gas and dust that heat up to millions of degrees as they spiral inward. These disks glow brighter than entire galaxies, making black holes some of the brightest objects in the universe, even though they're invisible. And sometimes, black holes shoot out jets of material at nearly the speed of light. These jets can stretch for thousands of light years, like cosmic blowtorches carving through space. But perhaps the most shocking thing about black holes is their role in the universe. They're not just destroyers, they're creators. The energy they release helps form stars and galaxies. Without black holes, we might not exist. They're the invisible architects of everything we see. Now for the most mind-blowing discovery. Black holes might not last forever. Stephen Hawking found that black holes slowly leak energy, like a pot of boiling water. This Hawking radiation means they evaporate over trillions of years. But here's the twist. When a black hole dies, it could release everything it ever swallowed. Stars, planets, even information. It's like the universe's ultimate recycling bin. But this creates a paradox. If information can't be destroyed, how does it escape a black hole? Scientists are still fighting over this. Some say it escapes through Hawking radiation. Others think it leaves imprints on the event horizon. The answer could rewrite physics as we know it. So, black holes are invisible giants that bend time, devour stars, and build galaxies. They're born from dying stars, hide in darkness, and shape the universe in ways we're just starting to understand. We hunt them by their effects, study them through math, and marvel at their power. They're not just empty voids. They're dynamic, mysterious, and full of surprises. Every discovery about them pushes the limits of human knowledge. What if I told you the man who literally invented the concept of black holes thought they were impossible? Albert Einstein, the genius who rewrote the rules of the universe, was terrified of his own discovery. Today, we're uncovering how Einstein's revolutionary insights accidentally predicted the most mysterious objects in space, and why he spent years trying to prove they didn't exist. This story will change how you see science, genius, and the universe itself. Einstein didn't just give us E equals mc squared. He gave us black holes. But here's the twist. He hated the idea. His theory of general relativity opened the door to these cosmic monsters. Then he spent decades trying to slam it shut. We're diving into the mind-bending journey of how Einstein's equations predicted something so wild that even he couldn't accept it. From war-torn Berlin to modern space telescopes, this is the story of how one man's greatest fear became science's greatest discovery. Here's the insane challenge Einstein faced. His own math was leading him somewhere he didn't want to go. In 1915, he published his theory of general relativity, describing gravity as the curvature of spacetime. But buried in those equations was a terrifying possibility. If you squeezed enough mass into a tiny point, spacetime would curve so violently it would create a bottomless pit from which nothing could escape. Einstein called this a catastrophe and believed nature must have a law against it. How do you deal with a theory that predicts something physically impossible? For Einstein, it wasn't just a scientific problem, it was a philosophical crisis. He'd built this beautiful theory explaining the universe, only to have it spit out monsters. Let's rewind to 1915. Einstein is in Berlin, working frantically to complete general relativity. He's been struggling for years to expand his special theory of relativity to include gravity. The breakthrough comes when he realizes gravity isn't a force pulling objects together. It's the bending of space-time itself. Imagine space-time as a trampoline. Put a bowling ball, like the sun, on it, and it creates a dent. Smaller objects like Earth roll around that dent. That's gravity. But Einstein's equations showed something else. If you make the bowling ball infinitely heavy and infinitely small, the dent becomes a bottomless hole. That's a black hole. Einstein saw this mathematically, but refused to believe it physically. He wrote to a friend saying, "The theory yields too much." He thought there must be some mechanism in the universe that prevented such extreme objects from forming. maybe quantum effects or something undiscovered would stop the collapse. He was so convinced that in 1939 he published a paper arguing that black holes couldn't exist in reality. Then came Karl Schwarzschild, a German physicist fighting in World War I. While Einstein was safely in Berlin, Schwarzschild was calculating artillery trajectories on the Russian front. In his spare time, he read Einstein's new theory and did something Einstein hadn't. He solved the equations exactly. Schwarzschild found that if you compressed any mass into a small enough radius, it would create an event horizon, a point of no return where gravity becomes infinite. Inside this boundary, not even light could escape. Schwarzschild sent his solution to Einstein, who was amazed. He called it a most admirable result. But here's the tragic part. Schwarzschild died just months later from a skin disease he contracted in the trenches. He never saw how his work would revolutionize physics. His solution gave us the first mathematical description of a black hole, including the Schwarzschild radius, the size of the event horizon. For a black hole with the mass of our Sun, that radius would be just 3 kilometers. Einstein was impressed, but still skeptical. He thought Schwarzschild's solution was just a mathematical curiosity, not something that could actually exist in nature. He believed that real stars would never collapse that way because of internal pressures and quantum effects. The debate raged for decades. In the 1930s, physicist Subramanian Chandrasekhar calculated that stars above a certain mass, about 1.4 times our Sun, would inevitably collapse under their own gravity after burning out. But when he presented this, the famous astronomer Arthur Eddington publicly humiliated him, saying, "I think there should be a law of nature to prevent a star from behaving in this absurd way." Eddington, like Einstein, couldn't accept that such extreme objects could exist. It wasn't until the 1960s that attitudes began to change. Physicist John Wheeler started seriously exploring what he called gravitationally collapsed objects. He realized that if Einstein's theory was correct, black holes weren't just possible, they were inevitable. Massive stars would collapse, and nothing could stop them. Wheeler coined the term black hole in 1967, and it stuck. But the real revolution came with modern technology. In the 1970s, astronomers discovered Cygnus X1, a powerful X-ray source that turned out to be a black hole devouring a nearby star. This was the first observational evidence that black holes were real. Then in 2015, the LIGO experiment detected gravitational waves, ripples in space-time caused by two black holes colliding. This confirmed Einstein's predictions in the most dramatic way possible. Einstein's insights didn't just predict black holes, they gave us the tools to understand them. His equations showed how black holes warp space-time, slow time, and trap light. They explained why black holes have event horizons and singularities, points where density becomes infinite and physics breaks down. Even though Einstein doubted black holes, his theory described them perfectly. One of the most mind-bending predictions is time dilation near black holes. Einstein's equations show that time slows down in strong gravitational fields. If you watched someone fall into a black hole, you'd see them freeze at the event horizon, fading slowly over billions of years. But for the person falling, time would pass normally until they hit the singularity. This isn't science fiction. It's a direct consequence of general relativity. Einstein also predicted that black holes could bend light, creating gravitational lensing. We've seen this with telescopes. Light from distant galaxies gets warped when it passes near a black hole, creating multiple images, or Einstein rings. This effect has helped us map black holes and confirm their existence. Perhaps the most shocking insight came from Stephen Hawking in the 1970s. Building on Einstein's work, he discovered that black holes aren't completely black. They emit radiation, now called Hawking radiation. This means black holes can slowly evaporate over trillions of years. Hawking showed that Einstein's theory, combined with quantum mechanics, leads to this bizarre result. Einstein would have been amazed. and probably a little horrified. Now for the most revolutionary twist. Einstein's equations might hold the key to understanding the entire universe. Modern physicists like Roger Penrose and Kip Thorne have used general relativity to explore what happens inside black holes. They found that singularities aren't just points of infinite density. They might be bridges to other universes or new dimensions. Some theories suggest that every black hole contains a new Big Bang, creating a baby universe. This sounds like science fiction, but it comes directly from Einstein's equations. The man who feared black holes might have accidentally given us the key to understanding the multiverse. Einstein's journey with black holes is a story of genius meeting its limits. He created the theory that predicted them, then spent years denying their existence. But in the end, his equations were right. Black holes are real, and they're exactly as strange as his math suggested. From Schwarzschild's first solution to modern gravitational wave detectors, Einstein's insights have guided our understanding of these cosmic monsters. He taught us that space-time is flexible, time is relative, and the universe is far stranger than we ever imagined. Einstein might not have liked black holes, but they're his greatest legacy. How do you hunt something that eats light? Something invisible, silent, and completely undetectable. Today, we're uncovering the brilliant tricks scientists use to find black holes, the universe's ultimate hide-and-seek champions. From X-ray fireworks to ripples in space-time, these methods are so clever, they'll make you feel like a cosmic detective. And trust me, the story of how we see the unseen is more mind-blowing than the black holes themselves. Black holes don't play fair. They're invisible, they don't reflect light, and they don't make a sound. For centuries, that made them impossible to study. But astronomers are stubborn. They invented ways to hunt these cosmic ghosts by looking for their victims, their leftovers, and even their shadows. Today, we're diving into the ingenious methods we use to detect what we cannot see, from space telescopes to gravitational wave detectors. This is how science turned darkness into discovery. Here's the insane problem. Black holes are designed to be undetectable. They trap everything, including light. It's like trying to find a black cat in a coal mine at midnight. For decades, astronomers had no tools to hunt them. Even Einstein thought they'd remain forever invisible. How do you study an object that actively hides from you? The challenge isn't just technical, it's philosophical. How do you prove something exists when it leaves no trace? Scientists had to get creative, developing methods that detect black holes indirectly by studying the chaos they create around them. It's like finding a burglar by the footprints they leave behind. Let's start with the most obvious clue. Black holes are messy eaters. When a black hole pulls in gas or dust from a nearby star, that material doesn't just vanish. It forms a swirling, superheated disk called an accretion disk. Friction heats this disk to millions of degrees, making it glow in X-rays. We can't see the black hole, but we can see the X-ray fireworks from its dinner. Take Cygnus X1, discovered in 1964. Astronomers noticed a bright X-ray source in the constellation Cygnus. They realized it was a black hole about 15 times heavier than our Sun, devouring material from a blue supergiant star. As gas spirals into the black hole, it heats up and emits X-rays so powerful they're detectable from Earth. This was the first solid proof that black holes exist. Cygnus X1 became the poster child for black hole research. But X-rays aren't the only clue. Black holes also affect nearby stars in strange ways. If a star orbits an invisible point in space at insane speeds, something massive must be there. That's how we found Sagittarius, a star, the supermassive black hole at the center of our galaxy. For years, astronomers watched stars whip around an empty spot at the Milky Way's core. One star, called S2, orbits at 15 million miles per hour, so fast that only an object 4 million times heavier than our Sun could hold it in place. That invisible object is Sagittarius, a star. Then there's gravitational lensing. Einstein predicted that massive objects bend space-time, which bends light too. When a black hole passes between us and a distant star or galaxy, it acts like a cosmic magnifying glass. distorting and multiplying the light behind it. We've seen this with telescopes. Light from distant galaxies gets warped into rings or arcs when it passes near a black hole. These Einstein rings are like fingerprints, revealing the black hole's presence even when we can't see it directly. But the real game changer came with gravitational waves. In 1916, Einstein predicted that massive accelerating objects, like colliding black holes, send ripples through space-time. These ripples stretch and squeeze space itself as they pass by. For decades, this was just theory. Then, in 2015, the LIGO experiment detected gravitational waves for the first time. They came from two black holes, colliding 1.3 billion light-years away. As they spiraled into each other, they released more energy in gravitational waves than all the stars in the universe combined. This was direct proof that black holes exist and that they collide. LIGO works with lasers and mirrors. It has two 4-kilometer-long arms arranged in an L shape. When a gravitational wave passes by, it slightly changes the length of the arms by less than the width of a proton. Detecting such a tiny change required technology so precise it's almost unbelievable. But LIGO did it, opening a whole new way to study black holes. Since 2015, we've detected dozens of black hole mergers, each one teaching us something new about these cosmic monsters. Another method is looking for quasars. These are incredibly bright objects at the centers of distant galaxies. For years, astronomers didn't know what powered them. Now we know quasars are supermassive black holes feeding on surrounding material. As gas falls into the black hole, it forms an accretion disk that glows brighter than entire galaxies. Some quasars are so bright we can see them from 13 billion light-years away, meaning they existed when the universe was just a baby. Quasars are like cosmic lighthouses, revealing the presence of supermassive black holes across the universe. We also use radio telescopes to study black holes. The Event Horizon Telescope, EHT, is a network of radio telescopes around the world that work together as one giant telescope the size of Earth. In 2019, the EHT released the first ever image of a black hole, a blurry orange ring around a dark center. That dark center is the black hole itself, or rather its shadow. The ring is light bent by the black hole's gravity. This image was of the black hole at the center of galaxy M87, 55 million light-years away. It's 6.5 billion times heavier than our Sun. The EHT proved we could see black holes directly, even if it's just their shadow. But perhaps the most mysterious detection method is studying jets. Some black holes shoot out powerful jets of material at nearly the speed of light. These jets can stretch for thousands of light-years, like cosmic blowtorches. We don't fully understand how they form, but they're another signpost pointing to black holes. The jets emit radio waves, X-rays, and even gamma rays, making them detectable across the electromagnetic spectrum. One of the most surprising detection methods came from studying pulsars. Pulsars are rapidly spinning neutron stars that emit beams of radio waves like cosmic lighthouses. In 1974, astronomers Russell Hulse and Joseph Taylor discovered a pulsar orbiting an invisible companion. By carefully timing the pulsar's signals, they realized the companion must be another neutron star or a black hole. Their observations provided indirect evidence for gravitational waves decades before LIGO detected them directly. Hulse and Taylor won the Nobel Prize for this work. Another clever method is looking for tidal disruption events. When a star wanders too close to a black hole, the black hole's gravity rips it apart in a process called spaghettification. As the stellar material spirals into the black hole, it emits a flare of radiation that telescopes can detect. These events are rare, but when they happen, they're like cosmic fireworks, announcing the presence of a black hole. We also use computer simulations to detect black holes. Astronomers create detailed models of how black holes should behave and compare them with observations. now called Hawking radiation. This happens when particle-antiparticle pairs pop into existence near the event horizon. Normally, they annihilate each other instantly, but near a black hole, one particle might fall in while the other escapes. The escaping particle is Hawking radiation. For stellar mass black holes, this radiation is too weak to detect. But for primordial black holes, tiny black holes that might have formed in the early universe, Hawking radiation could be detectable as gamma-ray bursts. If we find these, it would be direct proof of Hawking's theory and a whole new way to study black holes. So, detecting black holes is all about finding their fingerprints. We look for X-rays from their accretion disks, watch stars orbit invisible points, detect gravitational waves from their collisions, and even capture their shadows with planet-sized telescopes. Each method reveals a different aspect of these cosmic monsters. From Cygnus X1 to the EHT image, we've gone from guessing to seeing. Black holes might be invisible, but their effects are loud and clear. Thanks to these ingenious methods, we're finally uncovering the universe's darkest secrets. Picture a star so massive, it makes our sun look like a grain of sand. For millions of years, it burns brighter than entire galaxies. Then, in one violent, universe-shattering moment, it dies. But death isn't the end. It's a transformation. Today, we're uncovering how the most massive stars in the universe don't just fade away. They collapse into black holes. And trust me, the story of their final moments is more explosive, more terrifying, and more fascinating than any Hollywood blockbuster. Black holes aren't born out of nothing. They come from the violent deaths of the universe's biggest stars. When a star 20 times heavier than our sun runs out of fuel, it doesn't just go dark. It implodes with the force of 1 trillion atomic bombs. This collapse creates one of the most extreme objects in existence, a black hole. We're diving into the life cycle of massive stars, their dramatic deaths, and how they become the invisible giants that shape our universe. From nuclear fusion to supernova explosions, this is the story of stellar rebirth through destruction. Here's the mind-boggling challenge. How does something as vast as a star collapse into something as tiny as a black hole? Imagine crushing the Earth into the size of a marble. That's the kind of compression we're talking about. For decades, scientists struggled to understand this process. Stars are held up by nuclear fusion, which pushes outward against gravity. When fusion stops, gravity should win. But how does it create a black hole instead of just a dead star? The problem gets even more complex, because not all massive stars become black holes. Some become neutron stars, while others explode completely, leaving nothing behind. What determines a star's fate? And how does gravity overcome all other forces to create a point of infinite density? These questions puzzled astronomers for generations. Let's start with the life of a massive star. Stars are born from clouds of gas and dust called nebulae. Gravity pulls these clouds together, and as they collapse, the core heats up. When it reaches about 15 million degrees Celsius, nuclear fusion ignites. Hydrogen atoms fuse into helium, releasing enormous amounts of energy. This energy pushes outward, balancing gravity's inward pull. The star enters a stable phase called the main sequence, where it spends most of its life. Our sun is in this phase now, but massive stars live very differently. They burn hotter, brighter, and faster. A star 20 times heavier than the sun might live only 10 million years, compared to our sun's 10 billion years. The more massive the star, the shorter its life. Why? Because the intense gravity crushes the core, making fusion happen faster. It's like a car engine running at full speed. It burns out quickly. As the star ages, it fuses heavier elements. After hydrogen runs out, the core contracts and heats up, starting helium fusion. Helium fuses into carbon, then carbon into oxygen, neon, silicon, and finally iron. Each stage produces less energy than the last, so the star burns through elements faster and faster. This creates an onion-like structure, with iron at the core, surrounded by layers of lighter elements. Iron is the end of the line. Fusing iron doesn't release energy, it absorbs it. When the core becomes mostly iron, fusion stops. Without the outward push from fusion, gravity wins. The core collapses in less than a second. Imagine something the size of Earth collapsing into a city-sized ball. That's what happens. The core collapses from about 10,000 kilometers across to just 100 kilometers. This collapse is catastrophic. The outer layers of the star, no longer supported by the core, crash inward at nearly a quarter of the speed of light. When they hit the dense core, they bounce back, creating a shockwave that blows the star apart. This is a supernova, one of the most energetic events in the universe. For a few weeks, the supernova outshines entire galaxies. But what happens to the core? That's where black holes form. If the collapsing core is between about 1.4 and 3 times heavier than our Sun, it becomes a neutron star. Neutron stars are incredibly dense. A teaspoon of neutron star material weighs as much as a mountain. They're held up by neutron degeneracy pressure, a quantum mechanical effect that prevents further collapse. But if the core is heavier than about 3 solar masses, nothing can stop the collapse. Neutron degeneracy pressure fails, and the core collapses into a black hole. This is the Tolman-Oppenheimer-Volkoff limit, the maximum mass a neutron star can have. Beyond this, gravity wins completely. The collapse continues until the core is smaller than an atom, then smaller than a proton, and finally, a point of infinite density called a singularity. Around this singularity is the event horizon, the boundary beyond which nothing can escape. The size of the event horizon depends on the black hole's mass. For a black hole 10 times heavier than our Sun, the event horizon is about 30 kilometers across. But why do some stars form black holes while others don't? It comes down to mass and rotation. Stars heavier than about 20 solar masses are likely to form black holes. But rotation also plays a role. Rapidly rotating stars might form magnetars, highly magnetized neutron stars, instead of black holes. And if the star loses too much mass before collapsing, it might end up as a neutron star. Another factor is metallicity, the amount of elements heavier than hydrogen and helium in the star. Stars with low metallicity lose less mass during their lives, so they're more likely to form black holes. This is why black holes were more common in the early universe. We've seen this process happen in real time. In 1987, astronomers observed supernova 1987A in the Large Magellanic Cloud. It was the closest supernova in centuries. The star that exploded was about 20 times heavier than our Sun. Initially, scientists thought it would form a neutron star, but recent observations suggest it might have formed a black hole instead. In 2015, the LIGO experiment detected gravitational waves from 2 black holes colliding. These black holes were about 29 and 36 times heavier than our Sun. They must have formed from the deaths of extremely massive stars. The fact that we detected their merger tells us that black hole formation is common in the universe. But not all black holes form from single stars. Some form when 2 neutron stars merge. In 2017, LIGO detected gravitational waves from 2 neutron stars colliding. The merger created a black hole about 2.7 times heavier than our Sun. This shows that black holes can form in multiple ways. Another fascinating aspect is pair instability supernovae. For stars between about 130 and 250 solar masses, something even more dramatic happens. When the core gets hot enough, it produces gamma rays so energetic they create electron-positron pairs. This sudden loss of pressure causes the core to collapse, then explode with such force that the star is completely destroyed, leaving nothing behind. These stars are too massive to form black holes. They annihilate themselves instead. But for stars above 250 solar masses, even pair instability can't stop the collapse. They collapse directly into black holes without a supernova explosion. These are called direct collapse black holes, and they might explain how supermassive black holes formed so early in the universe. Now for the most shocking moment in a star's death, the birth of the event horizon. As the core collapses, it reaches a point where the escape velocity equals the speed of light. This is the Schwarzschild radius. Once the core collapses within this radius, the event horizon forms. From this moment on, nothing can escape. Not light, not matter, not even information. The event horizon isn't a physical surface. It's a boundary in space-time. Anything crossing it is doomed to hit the singularity. But here's the mind-bending part. From the outside, the collapse appears to freeze. Time slows down so much that we never actually see the event horizon form. We see the star get dimmer and redder as it approaches the Schwarzschild radius, but it never quite seems to cross it. This is because of gravitational time dilation. Time runs slower in stronger gravitational fields. So while the collapse takes less than a second from the star's perspective, from our perspective, it takes forever. The event horizon forms in our past, but we never see it form. This is why black holes are so mysterious. Their birth is hidden from us by the very laws of physics that govern them. So, the death of massive stars is a violent, transformative process. Stars, heavier than about 20 solar masses, burn through their fuel quickly, fuse elements up to iron, then collapse under their own gravity. If the collapsing core is heavier than about 3 solar masses, nothing can stop it from forming a black hole. The event horizon forms, hiding the singularity from view. But not all massive stars become black holes. Some become neutron stars, while others explode completely. The star's mass, rotation, and metallicity all play roles in determining its fate. This process is crucial for the universe because black holes seed galaxies, influence star formation, and recycle matter. Without the deaths of massive stars, the universe would be a very different place. What if I told you the universe is filled with millions of invisible cosmic vacuum cleaners, each heavier than our sun, but smaller than a city? They're lurking in every corner of our galaxy, silently devouring anything that strays too close. Today, we're uncovering the most common type of black hole in the universe, stellar black holes. These are the universe's hidden workhorses, and they're way more common than you think. By the end, you'll understand why these stellar graveyards hold the key to unlocking the universe's darkest secrets. Stellar black holes are the universe's ultimate recycling bins. Born from the deaths of massive stars, they're scattered across galaxies like cosmic tombstones. While supermassive black holes get all the fame, stellar black holes are the quiet majority, outnumbering their giant cousins by millions to one. We're diving into what makes these dark dwarfs tick, how we find them despite their invisibility, and why they're crucial to understanding the universe. From their formation to their destructive habits, this is the story of space's most common monsters. Here's the insane challenge. Stellar black holes are nearly impossible to spot. They're tiny, just a few miles across, and completely dark. Imagine trying to find a single grain of sand floating in the Pacific Ocean. That's what hunting stellar black holes feels like. Unlike their supermassive cousins, they don't have bright accretion disks or distort entire galaxies. Most float alone in space, invisible and silent. For decades, astronomers only knew they existed because of Einstein's equations. How do you study something that leaves no trace? The problem isn't just technical. It's like searching for ghosts that don't even rattle chains. Scientists had to get creative, developing methods to detect these cosmic ninjas by the subtle chaos they create around them. Let's start with what makes a stellar black hole. They form when stars between 20 and 100 times heavier than our sun die. When these stars run out of fuel, their cores collapse under gravity. If the collapsing core weighs more than about 3 suns, nothing can stop it. It becomes a black hole. These stellar black holes typically weigh between 5 and 50 times our sun's mass. For comparison, that's like crushing Mount Everest into something smaller than a marble. But here's the weird part. Stellar black holes are tiny. A 10 solar mass black hole would be only about 60 kilometers, 37 miles, across. You could fit one inside a small city, yet their gravity is so strong that nothing escapes their pull, not even light. That's why they're black. So how do we find them? The most common way is through X-ray binaries. These are systems where a black hole orbits a normal star. The black hole's gravity pulls material from its companion, forming an accretion disk. As this material spirals inward, it heats up to millions of degrees and emits X-rays. We detect these X-rays with space telescopes like Chandra. The first confirmed stellar black hole, Cygnus X1, was found this way. Discovered in 1964, it's about 15 times heavier than our Sun and orbits a blue supergiant star. As gas from the star feeds the black hole, it emits X-rays so powerful they're detectable from Earth. Cygnus X1 became the poster child for stellar black holes. For years, astronomers debated whether it was truly a black hole. But in the 1990s, precise measurements confirmed it. Today, we know of dozens of similar systems. Another detection method is astrometry, precisely measuring star positions. In 2022, astronomers using the Gaia Space Telescope found a stellar black hole called Gaia BH1. It's just 1,560 light-years away, our closest known black hole. How did they find it? They noticed a star wobbling as if pulled by an invisible companion. Calculations showed the companion must be a black hole about 10 times heavier than our Sun. What's wild is that this black hole isn't feeding on its companion. It's just orbiting silently, completely dark. This suggests there could be millions of quiet black holes we haven't detected yet. Gravitational lensing is another clever method. When a black hole passes between us and a distant star, its gravity bends the star's light, making it appear brighter or in multiple positions. By monitoring millions of stars for these lensing events, astronomers can estimate how many stellar black holes exist. Recent studies suggest our galaxy alone could contain 100 million stellar black holes. That's one black hole for every 1,000 stars. But not all stellar black holes are quiet. Some are among the most violent objects in the universe. When a black hole feeds rapidly, it can launch jets of material at nearly the speed of light. These jets emit radio waves and gamma rays detectable across the universe. One example is the microquasar 5404 Cygni. In 2015, it had a feeding frenzy, becoming one of the brightest X-ray sources in the sky. For 2 weeks, it emitted more energy than our Sun does in 1,000,000 years. Stellar black holes also play a crucial role in recycling matter. When they form from supernovae, they eject heavy elements into space. These elements, carbon, oxygen, iron, are the building blocks of planets and life. Without stellar black holes, we wouldn't exist. They're cosmic alchemists, turning stars into the ingredients for new worlds. Another fascinating aspect is black hole mergers. When two stellar black holes orbit each other, they spiral inward and eventually collide. This collision releases gravitational waves, ripples in space-time. The LIGO experiment has detected dozens of these mergers. One event, GW170814, involved black holes of 31 and 25 solar masses, colliding 1.8 billion light-years away. The collision released more energy in gravitational waves than all the stars in the observable universe combined. These mergers help us understand how black holes grow and evolve. But stellar black holes aren't just destroyers, they're creators too. Their extreme gravity triggers star formation in nearby gas clouds. When a black hole moves through a nebula, its gravity compresses the gas, causing it to collapse and form new stars. This positive feedback means black holes help create the very stars that will eventually form more black holes. It's a cosmic cycle of death and rebirth. We've also found stellar black holes in unexpected places. Globular clusters, dense groups of ancient stars, shouldn't have black holes, yet we've found several. The cluster NGC 6397 has a central black hole about 600 times heavier than our Sun. It's likely formed from multiple stellar black holes merging over billions of years. These intermediate mass black holes bridge the gap between stellar and supermassive black holes. Perhaps the most surprising discovery is that stellar black holes can have hair. According to classical physics, black holes should be featureless. Only mass, spin, and charge matter. But quantum mechanics suggests they might have subtle structures called quantum hair. If proven, this could solve the black hole information paradox, the puzzle of whether information swallowed by black holes is lost forever. Now for the most shocking revelation. Stellar black holes might be the seeds of supermassive black holes. Astronomers have found supermassive black holes in the early universe, less than 1 billion years after the Big Bang. How did they get so big so fast? The answer might be stellar black holes. In the early universe, stars were massive and metal poor. When they died, they formed black holes up to 100 times heavier than our Sun. These heavy seeds then grew rapidly by merging and feeding. Simulations show this process could create billion solar mass black holes in less than 1 billion years. Stellar black holes aren't just cosmic curiosities. They might be the ancestors of the giants that shape galaxies. So, stellar black holes are the universe's hidden majority. Born from massive star deaths, they're scattered across galaxies by the millions. We find them through X-ray binaries, gravitational lensing, and astrometry. They're tiny, but incredibly dense, with gravity strong enough to trap light. Despite their destructive power, they're crucial cosmic recyclers, creating the elements needed for life. They merge, creating gravitational waves that ripple across spacetime. And they might even be the seeds of supermassive black holes. Stellar black holes prove that the universe's most common monsters are also its most important architects. Imagine a black hole so rare it's practically a cosmic unicorn, bigger than stellar black holes but smaller than the giants at galaxy centers. For decades, astronomers hunted these missing links and found nothing. But now, we've finally caught them. Today, we're uncovering the mystery of intermediate black holes, the elusive middle children that could solve the biggest puzzle in astrophysics. And trust me, their story involves cosmic collisions, underwater explosions, and a breakthrough that's rewriting the history of the universe. Black holes come in 3 sizes: small, stellar, huge, supermassive, and the mysterious middle. Intermediate black holes, or IMBHS, weigh between 100 and 100,000 times our Sun's mass. They're the cosmic glue connecting stellar black holes to the monsters at galaxy centers. But for years, they were just theory. No solid proof, no direct observations. Now, thanks to space telescopes and gravitational wave detectors, we're finally finding them. We're diving into why IMBHS matter, how we hunt them, and why they're the key to understanding how supermassive black holes grew so big, so fast. Here's the cosmic headache. If supermassive black holes are billions of times heavier than our Sun, how did they form so quickly after the Big Bang? The universe is 13.8 billion years old, but we've spotted supermassive black holes when the universe was less than 1 billion years old. Stellar black holes, maximum 100 solar masses, couldn't grow that fast by merging or feeding. There had to be a middle step, bigger seeds. Enter IMBHS. But here's the catch. IMBHS are nearly impossible to find. They're too small to dominate galaxies like supermassive black holes, but too big to form from single collapsing stars. They're cosmic nomads, drifting through space without leaving obvious clues. For decades, astronomers searched and found only candidates, never proof. How do you hunt something that's too big to hide, too small to notice? Let's start with why IMBHS should exist. In the 1970s, theorists proposed them as the missing link. Stellar black holes form from single stars. Supermassive ones sit in galaxy centers. But what about black holes in between? IMBHS could form in 3 ways. 1. Runaway collisions in dense star clusters. 2. Mergers of stellar black holes. 3. direct collapse of giant gas clouds in the early universe. The first method is wild. In dense globular clusters, thousands of stars packed tighter than New York City, stars can collide and merge. If enough collide, they form a massive star that collapses into an IMBH. Simulations show this could create black holes up to 1,000 solar masses. But finding them, that's where it gets tricky. IMBHs don't have bright accretion disks like supermassive black holes. They're often quiet, floating in space without feeding. So astronomers got creative. Globular clusters are ancient, dense star clusters. Some show signs of central black holes. Take Omega Centauri, our galaxy's largest globular cluster. Stars near its core move at insane speeds, as if orbiting something invisible. Calculations suggest a 40,000 solar mass black hole lurks there, but it's not confirmed. The problem? Other things, like neutron stars, could cause the same motion. When a star wanders too close to a black hole, the black hole's gravity rips it apart. The stellar debris heats up, emitting a flare of X-rays and light. For supermassive black holes, TDES last months. For stellar ones, they last days. But for IMBHs, they last weeks. In 2006, astronomers spotted a TDE called Swift J1644+57. The flare lasted weeks, suggesting a black hole approximately 10,000 solar masses. It was the first strong IMBH candidate. This changed everything. In 2020, the LIGO/Virgo detectors caught gravitational waves from a collision unlike any before. Two black holes merged, one 85 solar masses, the other 66. The result was a 142 solar mass black hole. Why is this huge? Stellar black holes shouldn't grow beyond 50 solar masses, due to pair instability supernovae. But these were bigger. They were likely second-generation IMBHs formed from earlier mergers. This proved IMBHs exist and grow by colliding. Some objects emit X-rays brighter than stellar black holes, but dimmer than supermassive ones. These ULXS could be IMBHs feeding. The best example is HLX-1, Hyperluminous X-ray Source 1. Discovered in 2009, it's 300 million light-years away and emits X-rays 20 million times brighter than our Sun. Calculations show it's a 20,000 solar mass black hole. But here's the twist. It's not in a galaxy center. It's drifting alone, proving IMBHs can roam free. The 2020 gravitational wave event, GW190521, was a game-changer. The two colliding black holes were too big to be stellar, but too small to be supermassive. Their merger created a 142 solar mass black hole, the first definitive IMBH. But how did the originals form? One theory, they're primordial black holes born in the Big Bang. Another, they formed from direct collapse of giant gas clouds in the early universe. Either way, they solved the seed problem for supermassive black holes. IMBHs aren't just curiosities, they're cosmic architects. In the early universe, they could have been the seeds that grew into supermassive black holes. A 10,000 solar mass IMBH could grow to billions of solar masses in less than a billion years by feeding on gas and merging. This explains how supermassive black holes existed when the universe was young. IMBHs also influence galaxy evolution. When they merge, they release gravitational waves that can kick them out of galaxies. Rogue IMBHs might wander intergalactic space, invisible and silent. Some could even be captured by other galaxies, seeding new supermassive black holes. HLX-1 remains the most intriguing. IMBH. It's not in a cluster or galaxy center. It's alone. How did it form? One theory. It was ejected from a globular cluster after a merger. Another. It's the plus remnant of a dwarf galaxy shredded by a larger galaxy. Its existence proves IMBHS can survive independently, making them even harder to find. In 2010, a strange gamma-ray burst, nicknamed the Christmas burst, puzzled astronomers. It lasted longer than typical bursts and showed unusual chemical signatures. Later analysis suggested it was a neutron star colliding with an IMBH. The IMBH's gravity tore the neutron star apart, creating the burst. If confirmed, it's direct evidence of IMBHS interacting with other objects. New telescopes like the James Webb Space Telescope, JWST, and the Laser Interferometer Space Antenna, LISA, will revolutionize IMBH searches. JWST can detect faint light from IMBHS in the early universe. LISA, a space-based gravitational wave detector, will spot mergers involving IMBHs up to 10 million solar masses. Together, they'll map the IMBH population and solve the supermassive black hole origin puzzle. Now for the most mind-blowing twist. IMBHS might be everywhere, hiding in plain sight. In 2023, astronomers reanalyzed data from the Chandra X-ray Observatory and found dozens of IMBH candidates in dwarf galaxies. These galaxies are too small to host supermassive black holes, but they have central objects emitting X-rays like mini-quasars. The implications are staggering. If dwarf galaxies have IMBHS, then nearly every galaxy, including our Milky Way, might have started with an IMBH seed. This means IMBHs aren't just missing links, they're the ancestors of all supermassive black holes. The 2020 gravitational wave detection wasn't a fluke. It was the first glimpse of a cosmic process that built the universe's most massive structures. Intermediate black holes are no longer theory, they're real, and they're transforming our understanding of the universe. We found them through gravitational waves, X-ray flares, and star motions. They form from collisions, mergers, and direct collapse. They're the seeds that grew into supermassive black holes, solving the mystery of how these giants appeared so early in cosmic history. IMBHS roam galaxies, drift alone, and even get ejected into intergalactic space. They're the missing link that connects stellar black holes to the monsters at galaxy centers. With new telescopes, we're finally uncovering their secrets. One gravitational wave, one X-ray flare, one star cluster at a time. Picture an object so massive, it could swallow our entire solar system and still have room for more. Something heavier than billions of suns, yet smaller than Mercury's orbit. Today, we're diving into the true titans of the cosmos, supermassive black holes. These aren't just big, they're universe-shaping monsters that dictate how galaxies form, live, and die. And trust me, the story of how these giants grew so big, so fast, will make you question everything you thought you knew about space. Supermassive black holes are the bullies of the universe. They lurk at the heart of nearly every large galaxy, including ours. Weighing millions to billions of times our sun's mass, they're the most massive single objects in existence. But here's the mind-bender. They shouldn't exist. At least, not as big as they are, so soon after the Big Bang. We're uncovering how these cosmic engines work, how we found them, and why they're the key to understanding the universe itself. From their violent feeding habits to their role as galactic architects, this is the story of the universe's ultimate heavyweights. Here's the cosmic puzzle. Supermassive black holes are too big, too soon. We've spotted them when the universe was less than 1 billion years old, babies in cosmic time. But growing a billion solar mass black hole should take billions of years. Even if it fed non-stop at the maximum possible rate, it couldn't grow that fast. So how did they do it? This time problem has haunted astronomers for decades. It's like finding a fully grown skyscraper in a city that just appeared yesterday. The solution forces us to rethink how black holes form, how galaxies evolve, and even the laws of physics themselves. Without solving this, we can't understand how the universe we see today came to be. Let's start with scale. A stellar black hole might be the size of a city, a supermassive one. It's the size of our solar system. Yet, it's packed into a region smaller than the orbit of Mercury. Imagine crushing 4 billion suns into that space. That's Sagittarius A star, SGR A star, the black hole at the center of our Milky Way. It's small for a supermassive black hole, just 4 million solar masses. The biggest, TON 618, weighs 66 billion suns. If you replaced our Sun with TON 618, its event horizon would stretch past Neptune. Direct collapse is the leading solution for the earliest supermassive black holes. Simulations show that in the first few 100 million years, gas clouds could collapse under their own weight without fragmenting into stars. This would create black holes, 10,000 to 100,000 solar masses, right from the start. Supermassive black holes are easier to spot than smaller ones because they're messy eaters. As they pull in gas, dust, and stars, they form accretion disks that glow brighter than entire galaxies. These are quasars, the brightest objects in the universe. A single quasar can outshine 1,000 galaxies. The first quasar, 3C273, was discovered in 1963. It looked like a faint star, but emitted radio waves like nothing seen before. Calculations showed it was 2.4 billion light-years away and 100 times brighter than our entire galaxy. The only explanation? A supermassive black hole feeding furiously. Today, we've found over 1 million quasars. The most distant, J0313-1806, existed just 670 million years after the Big Bang. Its black hole weighs 1.6 billion suns. How did it get so big so fast? Direct collapse is the only plausible answer. Sagittarius, a star, our neighborhood monster. The closest supermassive black hole is Sega A star, 26,000 light-years away. For years, we tracked stars orbiting an invisible point at insane speeds. One star, S2, orbits at 15 million miles per hour, so fast it completes an orbit in just 16 years. In 2022, the Event Horizon Telescope, EHT, released an image of SGR-A star's shadow, a glowing ring of bent light around a dark center. It's the second direct image of a black hole, after M87 star in 2019. M87 star is 55 million light-years away and 6.5 billion times heavier than our Sun. The EHT image showed a bright orange ring, the accretion disk, bent by gravity into a perfect circle. The dark center is the black hole's shadow. This image confirmed Einstein's predictions and proved supermassive black holes exist beyond doubt. Many supermassive black holes shoot out jets of material at nearly light speed. These jets extend for thousands of light-years, emitting radio waves, X-rays, and gamma rays. How? The black hole's spin and magnetic fields launch material from the accretion disk like a cosmic slingshot. The best example is Centaurus A, a galaxy 12 million light-years away. Its jets stretch over 1 million light-years, longer than our galaxy is wide. When these jets hit intergalactic gas, they create shockwaves that trigger star formation. Supermassive black holes aren't just destroyers, they're creators. Supermassive black holes and galaxies grow together. As galaxies merge, their central black holes merge too. But here's the catch. When two black holes get close, they can't merge easily. They stall at about 1 light-year apart, the final parsec problem. Gravitational waves eventually push them together, but this can take billions of years. Black holes also regulate galaxy growth. When they feed, their jets and radiation heat up surrounding gas, preventing it from cooling and forming stars. This feedback stops galaxies from growing too big. Without it, galaxies would be 10 times larger than they are. Now for the most shocking discovery. Supermassive black holes might be everywhere. In 2023, the James Webb Space Telescope, JWST, found supermassive black holes in tiny, dwarf galaxies. These galaxies are too small to host such giants, yet there they are. One black hole in galaxy CEERS 1019 weighs 9 million suns, huge for a galaxy just 1/100th the Milky Way's size. This suggests supermassive black holes formed before their galaxies. They might be the seeds around which galaxies grew, not the other way around. If true, it flips our understanding of cosmic evolution. Black holes didn't just grow with galaxies, they created them. Supermassive black holes are the universe's ultimate powerhouses. They weigh billions of suns, fit into tiny spaces, and shape entire galaxies. We find them through quasars, star orbits, and now direct images. They form via direct collapse, mergers, or rapid feeding, solving the too big, too soon paradox. Their jets regulate star formation, and their mergers ripple spacetime. The JWST's discovery of supermassive black holes in dwarf galaxies suggests they're the seeds of galaxy formation itself. These aren't just cosmic monsters, they're the architects of everything we see. Imagine standing at the edge of a cosmic waterfall. One step forward, and you're swept into darkness forever. There's no coming back, no escape, no second chances. Today, we're exploring the event horizon, black hole's point of no return. It's not a physical surface, but a boundary in space-time where the laws of physics break down. And trust me, what happens at this edge will make you question reality itself. The event horizon is black hole's most terrifying feature. It's the invisible line where gravity becomes so strong that escape is impossible, not even for light. Cross it, and you're gone forever. But what is this boundary? How does it work? And why does it hide the universe's biggest secrets? We're diving into the science of the event horizon, from Einstein's predictions to modern observations. This is where space-time gets twisted. Time stands still, and the universe plays by its own rules. Here's the cosmic catch-22. The event horizon is fundamentally unknowable. Anything that crosses it vanishes from our universe, taking its secrets with it. We can't see it, touch it, or send probes to study it. It's like trying to map the inside of a vault that vaporizes anything entering. For decades, this made the event horizon a theoretical concept, math, not reality. Even Einstein doubted we'd ever prove it exists. How do you study something that actively erases evidence of its existence? The challenge isn't just technical, it's philosophical. The event horizon forces us to confront the limits of human knowledge. Let's start with the basics. The event horizon isn't a solid surface like a planet's crust. It's a boundary in space-time defined by gravity. Specifically, it's the distance from a black hole, where the escape velocity equals the speed of light. For Earth, escape velocity is 11 kilometers per second. For a black hole, at the event horizon, it's 299,792 kilometers per second, the speed of light. Nothing goes faster, so nothing escapes. The size of the event horizon depends on the black hole's mass. Carl Schwarzschild calculated this in 1916 using Einstein's equations. For a non-spinning black hole, the radius is simple. Class Rs frac CE2. That's the Schwarzschild radius. For our Sun, it'd be about 3 kilometers. For Sagittarius, a star, 4 million solar masses, it's 12 million kilometers, roughly 17 times the Sun's radius. For Ton 618, 66 billion solar masses, it's 200 billion kilometers, bigger than our solar system. But here's where it gets weird. From an outside perspective, nothing ever crosses the event horizon. As an object approaches, time slows down due to gravitational time dilation. To a distant observer, the object appears to freeze at the edge, fading slowly over billions of years. It gets redder and dimmer as light loses energy climbing out of the gravity well. Eventually, it becomes invisible. But from the object's perspective, it crosses the horizon in seconds, unaware anything special happened. This isn't an illusion, it's relativity in action. The event horizon also has bizarre effects on light. Light rays passing near it get bent so severely they orbit the black hole. At exactly 1.5 times the Schwarzschild radius, light can circle the black hole indefinitely in a region called the photon sphere. Closer in, light spirals inward. This creates the shadow we see in event horizon telescope images, a dark region surrounded by a bright ring of bent light. But the event horizon isn't just about gravity and light, it's about information. In 1976, Stephen Hawking dropped a bombshell. Black holes aren't eternal. They slowly evaporate via Hawking radiation. This created the black hole information paradox. If black holes evaporate, what happens to the information of everything that fell in? Quantum mechanics says information can't be destroyed. General relativity says it's lost forever. The event horizon is ground zero for this conflict. Hawking's solution? Information isn't destroyed. It's encoded on the event horizon. He proposed the holographic principle, suggesting the three-dimensional information inside a black hole is stored as two-dimensional data on its surface, like a hologram. This idea revolutionized physics, linking black holes to quantum gravity. We've also discovered that event horizons aren't featureless. In the 1970s, Jacob Bekenstein showed they have entropy, a measure of disorder. The more massive the black hole, the higher its entropy. This means event horizons store information, just like a computer hard drive. For a solar mass black hole, the entropy is enormous, about 10 to the 77th power times greater than the sun's. This led to the black hole thermodynamics field, treating event horizons as thermodynamic systems. But how do we study something we can't see? Indirectly, we watch material approaching the event horizon. As gas spirals inward, it heats up and emits X-rays. Just before crossing the horizon, it dims rapidly. We've seen this in X-ray binaries like Cygnus X1. The X-ray emission cuts off sharply as material vanishes from our observable universe. Gravitational waves also reveal event horizons. When black holes merge, their horizons oscillate like water droplets, emitting gravitational waves. The 2015 LIGO detection matched predictions for horizon dynamics, confirming their existence. The Event Horizon Telescope, EHT, gave us our first direct look. In 2019, it imaged M87 star's event horizon as a dark shadow 40 microarcseconds across, like spotting a donut on the moon. The image matched Einstein's predictions perfectly. In 2022, the EHT captured Sagittarius A star's shadow, confirming our own galaxy's black hole. But event horizons aren't just for black holes. In 2016, physicists proposed analog horizons in labs, using sound waves in superfluid helium or laser pulses in fiber optics. They created systems where information can't escape, mimicking event horizons. These experiments test Hawking radiation in controlled settings. Perhaps the wildest aspect is firewall paradox. In 2012, a team argued that event horizons might be firewalls, walls of high-energy particles that destroy anything crossing them. This contradicts general relativity, which says crossing should be uneventful. The debate rages on, highlighting how little we truly understand. Now for the most mind-bending twist. Event horizons might not exist. In 2014, Stephen Hawking published a paper suggesting apparent horizons instead. These are temporary boundaries that fluctuate due to quantum effects. Information isn't trapped forever. It slowly leaks out. This solves the information paradox, but breaks general relativity. Even more shocking, some theories propose that black holes are fuzzballs, tangled knots of quantum strings with no event horizon at all. If true, everything we thought we knew about black holes is wrong. The event horizon, black holes' defining feature, might be an illusion. The event horizon is black holes' most enigmatic feature. It's a boundary where gravity traps light, time freezes, and information faces oblivion. We've studied it through X-ray binaries, gravitational waves, and direct imaging. It has entropy, stores information, and challenges quantum mechanics. Yet, it remains fundamentally unknowable. Anything crossing it vanishes from our universe, taking its secrets with it. The event horizon isn't just a physical boundary, it's the edge of human knowledge, where physics as we know it ends. Imagine space itself as a rubber sheet. Now drop a bowling ball on it. It curves, right? Now drop something so heavy, it punches through the sheet. That's what black holes do to space-time. They don't just bend it, they twist, stretch, and tear it. Today, we're exploring how black holes warp the very fabric of reality. And trust me, what happens near these cosmic monsters will make you question everything you thought you knew about space, time, and gravity. Space-time isn't just empty space. It's the stage where the universe plays out. And black holes are the ultimate stage wreckers. They distort space-time so severely that time slows down, light bends into circles, and reality itself breaks down. We're diving into Einstein's wildest predictions, how black holes warp space-time, what that means for anything nearby, and why these distortions are the key to understanding gravity itself. From time dilation to frame dragging, this is where physics gets weird. Here's the mind-bending problem. Space-time distortion near black holes defies common sense. Time slows down. Light orbits in circles. Space itself flows like a river. These aren't sci-fi effects. They're real, measurable consequences of Einstein's relativity. But how do we study something so extreme? We can't visit a black hole. We can't recreate these conditions in labs. We're stuck observing from billions of light years away, piecing together clues from X-rays, gravitational waves, and distorted starlight. The challenge is translating these cosmic distortions into something we can understand, when the rules we live by no longer apply. Let's start with Einstein's big idea. Gravity isn't a force. It's curved space-time. Imagine space-time as a trampoline. Place a bowling ball, like our sun, on it, and it creates a dent. Roll a marble Earth nearby, and it orbits the dent. That's gravity. Now replace the bowling ball with a black hole. It doesn't just dent the trampoline, it punches through it, creating a bottomless pit. That's extreme space-time distortion. Near black holes, time doesn't just slow down, it crawls. This is gravitational time dilation. The stronger the gravity, the slower time passes. For someone hovering near a black hole's event horizon, seconds could mean years for distant observers. Take the planet Gargantua from Interstellar. It orbits a supermassive black hole. 1 hour there equals 7 years on Earth. That's not Hollywood magic. It's real physics. For a stellar mass black hole, the effect is even more extreme. Hover just above the event horizon, and a few seconds for you could mean centuries for the rest of the universe. We've proven this with GPS satellites. They orbit Earth where gravity is slightly weaker. Their clocks run 45 microseconds faster per day than clocks on Earth. If we didn't correct for this, GPS would misplace locations by 10 kilometers daily. Now imagine that effect amplified billions of times near a black hole. Black holes bend light so severely, they act like cosmic lenses. When light from a distant star passes near a black hole, the black hole's gravity curves its path. To us, the star appears in multiple places, or as a ring, called an Einstein ring. In 2020, astronomers spotted a star nicknamed Icarus behind a black hole 5 billion light-years away. The black hole's gravity bent Icarus's light, magnifying it 2,000 times. We saw a star 100 times farther than normally visible. This isn't just cool, it's a tool. Gravitational lensing lets us study the early universe, map dark matter, and even weigh black holes. Here's where it gets truly wild. Rotating black holes don't just curve space-time, they drag it around them. This is frame dragging, predicted by Einstein in 1918. Imagine space-time as honey. A spinning black hole stirs the honey, pulling everything around it in its rotation. We've measured this around Earth. The gravity probe B satellite found that Earth's rotation drags space-time by 0.000001 degrees per year. Near a black hole, the effect is violent. Space-time whirls like a tornado, pulling matter, light, and even time itself into the rotation. At one point, 5 times the Schwarzschild radius, gravity bends light so severely it orbits the black hole. This is the photon sphere, a region where light travels in circles. If you could stand there, you'd see the back of your head as light orbits the black hole. But the photon sphere is unstable. Like balancing a pencil on its tip, any disturbance sends light either into the black hole or escaping to infinity. This creates the bright ring in Event Horizon Telescope images, the last light that can escape. As you fall toward a black hole, gravity's pull on your feet is stronger than on your head. The difference tears you apart. Vertically, you stretch thinner and thinner until you're a stream of atoms. This is spaghettification. For stellar mass black holes, it happens long before you reach the event horizon. For supermassive ones, you might cross the horizon intact, only to be spaghettified inside. Either way, it's not a pleasant way to go. Rotating black holes have an extra region outside the event horizon called the ergosphere. Here, space-time is dragged so severely that nothing can stand still. Everything must rotate with the black hole. It's impossible to resist. The ergosphere also allows energy extraction. The Penrose process lets you steal rotational energy from the black hole, send a particle into the ergosphere, split it, and one piece falls in with negative energy, while the other escapes with more energy than you started with. It's like a cosmic perpetual motion machine, except it works. In 2015, LIGO detected gravitational waves from 2 black holes merging. As they spiraled together, they distorted space-time, sending waves across the universe at light speed. When they merged, the distortion peaked, releasing more energy than all stars combined. This proved Einstein right and gave us direct evidence of space-time distortion. Now for the most shocking revelation. Space-time distortion near black holes might create time machines. In 1991, physicist Kip Thorne proposed that rotating black holes could create closed, time-like curves, paths through space-time that loop back on themselves. In theory, you could follow such a path and arrive before you left. But there's a catch. Quantum effects likely destroy these curves before you could use them. Still, the math allows it. Black holes don't just distort space-time, they twist it into knots that could break causality itself. This isn't sci-fi, it's in Einstein's equations. Black holes might be the universe's ultimate time machines, if only we could survive them. Space-time distortion near black holes is physics at its most extreme. Time slows to a crawl, light bends into circles, space itself flows like a river. We see it in gravitational lensing, stellar orbits, and gravitational waves. These distortions prove Einstein's relativity and reveal gravity's true nature. From time dilation to frame dragging, black holes warp reality in ways that challenge our understanding. They're not just objects in space, they're architects of space-time itself. Imagine a place where density becomes infinite, time stops, and the laws of physics shatter like glass. A point smaller than an atom, yet heavier than a galaxy. Today, we're diving into the heart of darkness, the singularity. It's black hole's deepest secret, a cosmic enigma so extreme it makes scientists question reality itself. And trust me, what happens here will blow your mind wide open. The singularity is black hole's ultimate mystery. It's the point at the very center where matter is crushed into infinite density, where space-time ends, where Einstein's equations break down completely. We're uncovering what we know and what we don't know about this cosmic paradox. From Einstein's disbelief to modern quantum gravity theories, this is where physics meets its limits. Here's the cosmic crisis. The singularity shouldn't exist. According to general relativity, it's inevitable. Anything crossing an event horizon must hit this point of infinite density. But infinity isn't physical. It's a math error screaming, "Your theory is incomplete." Quantum mechanics hates infinities too. When we combine relativity and quantum theory, they contradict each other at the singularity. How do we study something that breaks both pillars of modern physics? It's like trying to map the center of a black hole with a flashlight that dies when it gets too close. The singularity forces us to confront the limits of human knowledge. Predicted singularities, but he refused to believe they were real. In 1939, he published a paper arguing that nature must prevent such pathological points. He thought quantum effects or rotation would stop the collapse before infinity. He was wrong. In 1965, Roger Penrose proved Einstein wrong. Using topology, Penrose showed that any collapsing massive object must form a singularity. It wasn't just possible, it was inevitable. This earned Penrose the 2020 Nobel Prize in Physics. But here's the problem. Penrose's proof assumes classical physics. At quantum scales, reality gets fuzzy. Quantum mechanics says particles can't be pinned down to exact points. They exist as probability clouds. So how can matter collapse to a point? This is where relativity and quantum mechanics collide. Cosmic censorship is Penrose's idea that nature hides singularities behind event horizons. Without this, the universe would have unpredictable points where physics breaks. But some quantum gravity models suggest naked singularities might exist. But quantum mechanics suggests you might not hit a point. Instead, you'd encounter a Planck star, a quantum foam of extreme density, or you'd tunnel into another universe via a wormhole, Einstein-Rosen bridge, or you'd be destroyed by a firewall of high-energy particles. We simply don't know. Hawking radiation, 1974, revealed a deeper problem. Black holes evaporate. When they do, what happens to information swallowed by the singularity? Quantum mechanics says information can't be destroyed. Relativity says it's lost forever. This is the black hole information paradox. In 2019, physicists used string theory to calculate that information does escape, encoded in quantum entanglement between Hawking radiation particles. But it's not settled. In 2012, a team led by Joseph Polchinski dropped a bombshell. The event horizon might be a firewall, a wall of high-energy particles that destroys anything crossing it. This contradicts relativity, which says crossing should be uneventful. If firewalls exist, Einstein's equivalence principle is wrong. The debate rages. The smallest meaningful length is the Planck length, 10 to the power of negative 35 meters. At this scale, quantum gravity dominates. Singularities likely aren't points. They're quantum foam bubbling with virtual particles. But we can't test this. Our best particle accelerator, LHC, probes down to 10 to the minus 19th meters, still 10 to the 16th times too large. Now for the most shocking twist. Singularities might not exist at all. In 2014, Stephen Hawking proposed apparent horizons, temporary boundaries that fluctuate due to quantum effects. Information isn't trapped, it slowly leaks out. This eliminates singularities but breaks general relativity. Even wilder, loop quantum gravity suggests singularities are bounces. Instead of infinite density, matter reaches Planck density and rebounds, creating a white hole that ejects everything. If true, black holes are cosmic recycling machines. Matter falls in, hits the bounce point, and explodes out as a white hole. Some theories even link this to the Big Bang. Our universe might be a black hole bounced from another universe. The singularity isn't an end, it's a bridge. The singularity is physics' greatest mystery. It's where density becomes infinite, time ends, and our laws break down. Einstein denied it. Penrose proved it. Quantum mechanics rejects it. We've proposed fuzzballs, bounces, and holograms to explain it. But the truth remains hidden behind event horizons. Singularities force us to confront the limits of knowledge. They're not just cosmic curiosities. They're the key to unifying physics. Until we solve the singularity, we don't truly understand gravity, time, or reality itself. What if I told you that near a black hole, you could watch the entire future of the universe unfold in what feels like minutes to you? Or that 1 hour near a black hole could mean 7 years pass for everyone else? Today, we're diving into black holes' most mind-bending power, their ability to warp time itself. And trust me, this isn't sci-fi. It's real physics that'll make you question everything you thought you knew about reality. Black holes don't just bend space, they twist time into knots. Near these cosmic monsters, time slows down, stretches, and even stands still. We're uncovering how gravity near black holes manipulates time in ways Einstein predicted, but we're only now proving. From the ticking of clocks to the aging of stars, time dilation near black holes reveals gravity's true nature. And it's not just theory. We see it happening right now in our own galaxy. Here's the cosmic headache. Time dilation near black holes defies common sense. How can time run at different speeds depending on where you are? It sounds impossible, but Einstein's relativity proves it's real. The problem? We can't visit black holes to test this directly. We're stuck observing from billions of light years away, piecing together clues from distorted starlight and gravitational waves. How do we study something that makes time itself behave erratically? The challenge is translating these extreme time effects into something we can understand, when the very concept of now becomes relative. Let's start with Einstein's revolutionary idea. Gravity isn't a force, it's curved spacetime. And where spacetime curves, time slows down. This is gravitational time dilation. The stronger the gravity, the slower time passes. Near a black hole, this effect becomes extreme. Imagine 2 clocks, one on Earth, one in space. The space clock runs slightly faster because gravity is weaker. We prove this daily with GPS satellites. Their clocks run 45 microseconds faster per day than Earth clocks. Without correcting for this, GPS would misplace locations by 10 kilometers daily. Now, amplify that effect billions of times near a black hole. For a stellar mass black hole, 10 times our sun's mass. Time dilation becomes severe near the event horizon. Hover just above it, and time for you passes 100,000 times slower than for distant observers. 1 second for you equals over a day for them. Fall in, and to the outside universe, you appear frozen at the edge forever, fading slowly over billions of years. We see this in X-ray binaries like Cygnus X1. Material from its companion star spirals toward the black hole. As it approaches the event horizon, its light dims and reddens. This gravitational redshift happens because time slows so much that light waves stretch out, losing energy. We've measured this redshift, confirming time dilation in action. Supermassive black holes have larger event horizons, so gravity increases more gradually. Near Sagittarius, a star, our galaxy's 4 million solar mass black hole, time dilation is less extreme, but still significant. Stars orbiting close to it experience measurable time effects. Take star S2. It orbits S-star A star at 15 million miles per hour. At its closest approach, 120 times the Earth-Sun distance, time for S2 runs 20% slower than for us. We've observed this through its light, shifted toward red wavelengths due to time dilation. This isn't just theory, it's direct observation of time slowing near a black hole. As light climbs out of a black hole's gravity well, it loses energy. Since light speed is constant, it can't slow down. Instead, its wavelength stretches, shifting toward red. This gravitational redshift is direct evidence of time dilation. We've measured this in quasars. Some quasars show redshifts so extreme they suggest time near the black hole runs 10 times slower than in the rest of the universe. For a quasar 10 billion light-years away, we're essentially seeing its past in extreme slow motion. At one point, 5 times the Schwarzschild radius, gravity bends light into circular paths. This is the photon sphere. Here, time dilation becomes infinite. Light orbits forever, trapped in a loop. If you could hover here, you'd see the back of your head as light circles the black hole. But it's unstable. Any disturbance sends light either into the black hole or escaping to infinity. Rotating black holes drag spacetime around them, a phenomenon called frame dragging. Near a spinning black hole, spacetime whirls like a tornado. This affects time too. Clocks in the direction of rotation run faster than those against it. We've measured frame dragging around Earth. The gravity probe B satellite found Earth's rotation drags spacetime by 0.000001 degrees per year. Near a fast-spinning black hole, the effect is violent. Spacetime whips around so severely that standing still is impossible. You're forced to rotate with the black hole. Here's where it gets truly wild. Rotating black holes might allow time travel. In 1991, Kip Thorne showed that a spinning black hole's frame dragging could create closed time-like curves, paths through spacetime that loop back on themselves. Follow such a path, and you could return before you left. But there's a catch. Quantum effects likely destroy these curves before they form. Even if they exist, they'd be unstable. Still, the math allows it. Black holes might be nature's time machines, if only we could survive them. Stephen Hawking explored this in the 1990s. He suggested that if you flew a spaceship around a fast-spinning black hole, you could emerge in your own past. But he later added a chronology protection conjecture. Quantum effects would prevent time travel to avoid paradoxes. The debate continues. Time dilation near black holes challenges our concept of now. If time runs at different speeds, depending on location, is there a universal present? Einstein said, no, now is relative. Black holes prove this dramatically. Near one, your now could be someone else's distant future. Now for the most shocking revelation. Black holes might be natural time machines to the future. Here's how. Hover near a black hole's event horizon for a while, then return. For you, only days passed. For Earth, centuries flew by. You've effectively traveled to the future. This isn't theory. It's allowed by relativity. The only problem? Surviving the journey. But if you could ride a stable orbit just outside the event horizon of a supermassive black hole like M87 star, 6.5 billion solar masses, you'd experience significant time dilation without being torn apart. A year there could mean 100 years on Earth. Black holes aren't just cosmic destroyers. They're gateways to the future. And while traveling to the past might be impossible, traveling forward is built into the fabric of space-time itself. Time dilation near black holes is one of relativity's most profound predictions and most extreme effects. Time slows to a crawl near event horizons. Light stretches into redshift. Space-time itself drags into whirlpools. We see it in quasar flickering, stellar orbits, and gravitational waves. These effects prove Einstein right and reveal gravity's true nature. From GPS satellites to future time travel, time dilation near black holes shows that time isn't absolute. It's flexible, relative, and deeply connected to gravity. Black holes don't just warp space, they warp time itself. Picture a cosmic hurricane made of superheated gas, spinning at nearly the speed of light, and glowing brighter than a trillion suns. This isn't science fiction. It's an accretion disk, the black hole's dinner plate. Today, we're diving into these cosmic feeding frenzies, where matter gets torn apart, heated to millions of degrees, and launches jets that reshape galaxies. And trust me, what happens in these swirling death spirals is more violent and more beautiful than anything else in the universe. Accretion disks are black holes' most visible and violent feature. They're swirling rings of gas, dust, and shredded stars, spiraling toward the event horizon. As matter falls inward, friction heats it to extreme temperatures, making accretion disks some of the brightest objects in space. We're uncovering how these cosmic engines work, why they glow so fiercely, and how they turn black holes from invisible voids into brilliant beacons. From stellar mass black holes to supermassive giants, accretion disks reveal how black holes grow, feed, and influence everything around them. Here's the cosmic puzzle. Accretion disks shouldn't exist, at least not as we see them. Black holes have no surface, so matter shouldn't collide and glow. Yet, accretion disks outshine entire galaxies. How? The answer lies in extreme physics, where friction, magnetism, and gravity battle in ways we're only beginning to understand. The challenge is modeling these disks. They're too far to observe directly, too complex to simulate fully, and too violent to recreate in labs. We're stuck piecing together clues from X-rays, radio waves, and gravitational waves, like detectives solving a cosmic crime with scattered evidence. Let's start with the basics. An accretion disk forms when matter, gas, dust, or even stars, gets too close to a black hole. The black hole's gravity pulls the matter inward, but because of angular momentum, it can't fall straight in. Instead, it spirals, forming a flat, rotating disk. Think of water swirling down a drain. Only this drain has the gravity of billions of suns. Why do accretion disks glow? Friction. As matter orbits, adjacent layers rub against each other. This friction converts orbital energy into heat. But here's the catch. Space is nearly frictionless. So how does this happen? The answer is magnetorotational instability, MRI. Magnetic fields in the disk get tangled by differential rotation. Inner parts orbit faster than outer parts. This creates turbulence, which acts like viscosity, generating friction. MRI was proposed in 1991 and is now the leading theory for accretion disk heating. For supermassive black holes, accretion disks become cosmic powerhouses. When fed aggressively, they outshine their host galaxies. These are quasars, the brightest objects in the universe. A single quasar can emit 1,000 times more energy than our entire Milky Way. Take quasar 3C273, 2.4 billion light-years away. Discovered in 1963, it was the first identified quasar. Its accretion disk is so bright, it's visible in amateur telescopes. How? The black hole, 6 billion solar masses, feeds on gas, heating the disk to 10 million degrees. The disk glows across the electromagnetic spectrum, from radio waves to gamma rays. Some accretion disks launch relativistic jets, beams of plasma shooting out at near light speed. When a jet points toward Earth, we see a blazar. Blazars are even brighter than quasars because their jets are aimed at us. Blazar TXS 0506 plus 056, for example, emits gamma rays so energetic they challenge our understanding of particle physics. Stellar mass black holes, X-ray binaries. For stellar mass black holes, accretion disks form in binary systems. The black hole pulls material from a companion star. This creates an X-ray binary. The first discovered, Cygnus X1, has a 15 solar mass black hole feeding on a blue supergiant. As gas spirals in, it heats to 100 million degrees, emitting X-rays detectable from Earth. We see variability in these disks. Some flicker in milliseconds as clumps of matter hit the inner disk. Others show quasi-periodic oscillations, QPOS, regular pulses that reveal the disk's size and the black hole's spin. The Event Horizon Telescope, EHT, imaged the accretion disk of M87 star in 2019. The bright orange ring isn't the black hole. It's the disk's light bent by gravity. The dark center is the black hole's shadow. This image confirmed decades of predictions about accretion disk structure. Accretion disks aren't steady. They flicker, flare, and change brightness. Why? Instabilities in the disk cause matter to fall in clumps rather than smoothly. When a large clump hits the inner disk, it creates a flare. We see this in X-ray binaries like GRS 1915 plus 105, which shows chaotic variability every few seconds. A black hole's spin affects its accretion disk. Fast-spinning black holes drag spacetime, pulling the disk inward. This allows matter to orbit closer, releasing more energy. The spin also determines jet power. Faster spins launch stronger jets. We measure spin using X-ray spectroscopy. For example, Cygnus X1 spins at 95% of its maximum possible speed, making it one of the fastest spinning objects known. The Eddington limit is the maximum rate a black hole can feed before radiation pressure blows material away. But some disks exceed this. These super Eddington accretors are hyperluminous. Stellar mass black holes like SS433 accrete so fast they outshine supermassive ones. Their disks are thick and puffed up, with powerful outflows. Now for the most shocking discovery. Accretion disks might create the building blocks of life. In 2023, astronomers found complex organic molecules, like methanol and acetic acid, in the accretion disk of a young stellar object. These molecules are precursors to amino acids, the building blocks of life. How? Shockwaves in the disk trigger chemical reactions, turning simple gas into organic compounds. This suggests accretion disks aren't just destructive, they're cosmic factories where the ingredients for life are forged. If this happens around stellar mass black holes, it could mean life's precursors are scattered throughout the universe, created in the violent disks of black holes. The same process that powers quasars might also seed life. Accretion disks are black holes' dynamic, violent, and brilliant companions. They form when matter spirals inward, heated by friction and magnetism. They power quasars, launch jets, and outshine galaxies. We study them across the electromagnetic spectrum, from radio waves to gamma rays. Their variability reveals black hole spin and feeding habits. Most surprisingly, they might create the building blocks of life. Accretion disks turn black holes from invisible voids into cosmic engines, shaping galaxies, launching jets, and possibly seeding life itself. Imagine a beam of energy shooting through space at 99.9% the speed of light, so powerful it could vaporize our solar system in seconds. These aren't sci-fi weapons. They're relativistic jets, black holes' cosmic death rays. Today, we're uncovering how these invisible monsters launch the most destructive and energetic forces in the universe. And trust me, what you'll learn about these cosmic blowtorches will change how you see black holes forever. Relativistic jets are black holes' ultimate superpower. Narrow beams of plasma shooting from their poles at near light speed, stretching across millions of light years. They outshine galaxies, reshape cosmic structures, and carry more energy than 1 trillion atomic bombs. We're diving into how black holes create these jets, why they're so focused, and how they've become the universe's most powerful particle accelerators. From stellar mass black holes to supermassive giants, these jets reveal the violent, creative, and terrifying side of cosmic evolution. Here's the cosmic mystery. How do black holes, objects defined by their inward pull of gravity, shoot matter outward at near light speed? It's like watching a black hole inhale and exhale simultaneously. The physics defies intuition. Gravity pulls everything in, yet jets escape. How? The answer involves twisted magnetic fields, spinning black holes, and plasma physics so extreme we can't recreate it in labs. The challenge? We're studying jets billions of light years away, relying on X-ray telescopes, radio antennas, and gravitational wave detectors to piece together clues. Jets are black holes' most visible feature, yet their creation remains one of astrophysics' greatest puzzles. Let's start with what relativistic jets are. They're narrow, focused streams of ionized gas, plasma, ejected from the poles of black holes. They travel at 90 to 99.9% of light speed and can extend for thousands of light years, far beyond their host galaxies. Jets emit radiation across the spectrum: radio waves, X-rays, and even gamma rays. Jets tap into the black hole's rotational energy. A spinning black hole has enormous rotational energy, up to 29% of its total mass energy. The Blandford-Znaiec mechanism can extract this energy with 50% efficiency. For comparison, nuclear fusion converts 0.7% of mass to energy. Jets are the universe's most efficient energy converters. In our galaxy, stellar mass black hole SS433 shoots jets at 26% light speed, slow for relativistic jets, but still 78,000 kilometers per second. Its jets precess, wobble, like a spinning top, completing a cycle every 162 days. Why? The black hole's accretion disk is tilted, causing the jets to sweep across space like a cosmic lawn sprinkler. Now for the most shocking discovery: jets might seed life. In 2023, astronomers found complex organic molecules, like methanol and acetic acid, in the jets of protostellar object HH212. These molecules are precursors to amino acids. How? Jets shock interstellar gas, triggering chemical reactions that turn simple molecules into life's building blocks. If this happens around black holes, it means jets, cosmic death rays, might also be cosmic gardeners, spreading the ingredients for life across the universe. The same forces that can vaporize planets might also create them. Relativistic jets are black holes' most extreme phenomenon. Narrow beams of plasma, shot from poles at near light speed, powered by spinning black holes and magnetic fields. We see them in quasars, blazars, and microquasars. They outshine galaxies, regulate star formation, and spread heavy elements. Their creation remains mysterious, but observations from Chandra, Fermi, and the EHT are revealing their secrets. Most surprisingly, jets might carry life's building blocks. These cosmic death rays aren't just destroyers, they're creators, shaping galaxies and possibly seeding life across the cosmos. Imagine a cosmic architect, so powerful, it builds galaxies while sitting at their center. Something so small, it could fit in our solar system, yet so massive, it controls billions of stars. Today, we're uncovering how black holes aren't just residents of galaxies, they're their creators, regulators, and destroyers. And trust me, the story of how these invisible monsters shape the universe will change everything you thought you knew about cosmic evolution. Black holes and galaxies aren't just neighbors, they're locked in a cosmic dance that's lasted 13 billion years. Supermassive black holes sit at the heart of nearly every large galaxy, including ours. They don't just float there, they actively shape how galaxies form, grow, and die. We're diving into this mysterious relationship, how black holes seed galaxies, regulate their growth, and even trigger their star formation. From the early universe to today, this is the untold story of cosmic co-evolution. Here's the cosmic puzzle. How can something smaller than our solar system control a galaxy spanning trillions of miles? Black holes make up just 0.1% of a galaxy's mass, yet they dictate its fate. How? The answer involves extreme physics, where gravity, radiation, and magnetism battle in ways we're only beginning to understand. The challenge? We're studying this relationship across cosmic time, piecing together clues from ancient light, computer simulations, and space telescopes. It's like trying to understand how a single brick shapes an entire skyscraper, while the building is still being constructed. Let's start with a shocking fact. Nearly every large galaxy has a supermassive black hole at its center. The Milky Way has Sagittarius, a star. Andromeda has one too. Even tiny dwarf galaxies often host central black holes. This isn't coincidence. It's evidence of a deep connection. In 2000, astronomers discovered a pattern called the M-sigma relation. It links a black hole's mass to its galaxy's properties, specifically the velocity dispersion, how fast stars move in the galaxy's center. The formula is simple. Heavier black holes live in galaxies with faster moving stars. Why does this matter? It proves black holes and galaxies evolve together. A black hole doesn't just grow randomly. Its growth is tied to the galaxy's growth. When the galaxy forms more stars, the black hole feeds more. When the black hole grows, it affects the galaxy. They're cosmic partners. This energy blows gas away or prevents it from cooling. Since gas is needed to form stars, feedback effectively shuts down star formation. It's like a cosmic thermostat. When a galaxy grows too fast, the black hole turns down the heat by blowing gas away. What turns blue galaxies red? Black hole feedback. When a black hole feeds aggressively, it quenches star formation. The galaxy stops making new stars and ages passively. We see this in elliptical galaxies, giant, red, and dead. Their central black holes are often massive and inactive, having done their job. The Perseus cluster is a galaxy cluster, 240 million light-years away. At its center is a supermassive black hole feeding actively. Its jets inflate enormous bubbles in the surrounding gas. These bubbles create sound waves. Yes, sound in space, with a frequency 57 octaves below middle C. These waves heat the gas, preventing it from cooling and forming stars. Without this feedback, the cluster would have 10 times more stars than it does. The James Webb Space Telescope, JWST, has found galaxies in the early universe that challenge our understanding. Some galaxies, like CEERS 1019, are less than 1 billion years old, but already host massive black holes. How? Either galaxies form inside dark matter halos, invisible spheres of dark matter that provide gravitational scaffolding. Black holes sit at the center of these halos. The halo's mass influences the black hole's growth. Larger halos provide more gas, allowing both the galaxy and black hole to grow bigger. This explains the M-sigma relation. Larger halos make larger galaxies with faster moving stars, which host larger black holes. JWST's discovery of overmassive black holes in small galaxies supports the idea that black holes seeded galaxy formation. They might have acted as seeds around which gas collected, forming the first galaxies. Now for the most shocking revelation. Black holes might be the reason galaxies exist at all. In 2023, JWST found galaxies like Jade's GSZ 13-0, just 325 million years after the Big Bang. These galaxies have black holes so massive they shouldn't exist yet. The only explanation? These black holes formed before the galaxies, pulling in gas that became the galaxy's stars. In this view, black holes aren't just residents. They're the foundations of galaxies. They're cosmic anchors that gather matter, trigger star formation, and regulate growth. Without black holes, galaxies might not have formed the way they did. The universe's structure, its spirals, ellipticals, and clusters, might owe its existence to these invisible giants. Black holes and galaxies are inseparable partners in cosmic evolution. They grow together through mergers and accretion, linked by the M-sigma relation. Black holes regulate galaxy growth through feedback, quenching star formation when galaxies get too big. Evidence from the Perseus cluster, computer simulations, and JWST all confirm this relationship. Most surprisingly, black holes might have seeded galaxy formation itself. They're not just destructive forces. They're cosmic architects that shape the universe's structure. Without black holes, galaxies as we know them wouldn't exist. Picture the universe as a vast, invisible ocean. Now imagine something so violent happening billions of light years away that it sends ripples through this ocean, ripples that stretch and squeeze space itself as they pass by. Today, we're uncovering gravitational waves, Einstein's final prediction that took 100 years to prove. These ripples in spacetime are black holes' most elusive signature, and they're revolutionizing how we see the cosmos. And trust me, the story of how we caught these cosmic waves will blow your mind. Gravitational waves are black holes' hidden language. When black holes collide or merge, they shake spacetime itself, sending waves across the universe at light speed. For decades, these waves were just theory, math on a chalkboard. Now, we detect them regularly, opening a new window into the universe. We're diving into how gravitational waves work, how we catch them, and why they're transforming astronomy. From Einstein's doubts to LIGO's Nobel-winning detection, this is the story of space-time in motion. Here's the cosmic catch-22. Gravitational waves are incredibly faint. By the time they reach Earth, they stretch space by less than the width of an atom. Detecting them is like measuring the distance to a nearby star and noticing it changed by a hair's width. How do you build a machine that sensitive? For 50 years, scientists tried and failed. The technology didn't exist. The challenge wasn't just engineering, it was believing these waves were detectable at all. Even Einstein doubted we'd ever catch them. How do you hunt something that distorts reality so subtly it's buried in cosmic noise? Let's start with Einstein's 1915 revolution. His general relativity said gravity isn't a force, it's curved space-time. Massive objects like black holes warp space-time like a bowling ball on a rubber sheet. Einstein realized that if these objects move violently, say, two black holes orbiting each other, they should create ripples in space-time, gravitational waves, but he thought they'd be too weak to ever detect. The change is tiny, 1/10,000th the width of a proton. To detect this, LIGO needs extreme isolation from vibrations, earthquakes, trucks, even ocean waves. The mirrors hang as pendulums in vacuum chambers, suspended by fused silica fibers thinner than human hair. On September 14th, 2015, LIGO made history. It detected gravitational waves from two black holes colliding 1.3 billion light-years away. One was 29 solar masses, the other 36. They merged into a 62 solar mass black hole, releasing 3 solar masses of energy as gravitational waves. That's more energy than all stars in the observable universe combined, released in 0.2 seconds. In 2017, LIGO detected gravitational waves from 2 neutron stars merging, GW 170817. This time, telescopes saw it too. Fermi Space Telescope caught a gamma-ray burst seconds later. Then, 70 observatories studied the event across light, radio, and X-rays. This was multi-messenger astronomy, combining gravitational waves with light. Now for the most shocking discovery. Gravitational waves might reveal the universe's first moments. In 2023, NanoGrav, a project using pulsars as cosmic clocks, found evidence for a gravitational wave background, a low-frequency hum filling the universe. This could be waves from countless supermassive black hole mergers over cosmic time. But some scientists think it might be from cosmic inflation, ripples from the Big Bang itself. If confirmed, this would be the first direct evidence of inflation, proving the universe expanded faster than light in its first fraction of a second. Gravitational waves aren't just telling us about black holes, they're whispering secrets from the dawn of time. Gravitational waves are spacetime's ripples, created when black holes collide or neutron stars merge. Predicted by Einstein in 1915, they remained undetected until LIGO's breakthrough in 2015. Now, detectors worldwide catch these waves regularly, revealing black hole masses, spins, and populations. Multi-messenger astronomy combines gravitational waves with light, giving a full picture of cosmic events. Future detectors like LISA will explore supermassive black holes and the early universe. Gravitational waves have opened a new sense for humanity. We can now hear the universe's most violent events, transforming our understanding of black holes and cosmic evolution. What if I told you black holes aren't completely black, that they actually glow, faintly, invisibly, like dying embers in the cosmic night? Today, we're uncovering Stephen Hawking's wildest idea, that black holes slowly evaporate. And trust me, this discovery is so bizarre. It rewrites the rules of physics and challenges everything we thought we knew about the universe. Black holes are supposed to be cosmic prisons. Nothing escapes, not even light. But in 1974, Stephen Hawking turned that idea upside down. He predicted that black holes actually leak energy, slowly shrinking over trillions of years, until they vanish. This is Hawking radiation, and it's one of the most mind-bending concepts in physics. We're diving into how something that traps everything can somehow emit radiation, why this discovery created a crisis in science, and what it means for the fate of black holes across the universe. Here's the cosmic paradox. Black holes, by definition, don't let anything out. Their gravity is so strong that escape is impossible. Yet Hawking's math showed they must emit radiation. How? The answer involves quantum mechanics and general relativity, two theories that don't play well together. The challenge? Hawking radiation is so faint that we've never directly detected it. It's like trying to hear a whisper in a hurricane. For decades, physicists have debated whether Hawking's idea is real or just a beautiful theory. And if it is real, it creates an even bigger problem. The black hole information paradox. How can something that swallows information forever then release it when it evaporates? This puzzle has haunted physics for 50 years. Let's start with the basics. In 1915, Einstein gave us general relativity, which describes gravity as curved spacetime. Black holes are the ultimate expression of this, points where spacetime curves infinitely. Then came quantum mechanics in the 1920s, which describes particles and forces at tiny scales. The problem? These two theories don't mix. Relativity rules the big stuff, planets, galaxies. Quantum rules the small stuff, atoms, particles. Black holes are where both matter, and that's where things get weird. Quantum mechanics says empty space isn't really empty. It's a seething foam of virtual particles popping in and out of existence. These are particle-antiparticle pairs, like electron-positron, that appear, annihilate each other, and vanish, all in a fraction of a second. Normally, we never notice them because they cancel out instantly. But near a black hole's event horizon, something strange happens. In 1974, Hawking was thinking about quantum effects near black holes. He realized that if a virtual particle pair appears right at the event horizon, one particle could fall in while the other escapes. The escaping particle becomes real, carrying energy away from the black hole. To an outside observer, it looks like the black hole is emitting radiation. But here's the catch. The energy for this radiation comes from the black hole itself. By losing energy, the black hole loses mass. It slowly shrinks. Imagine the event horizon as a one-way membrane. Virtual particle pairs appear constantly. Normally, they annihilate each other. But if they appear at the horizon, gravity can pull one particle in while the other escapes. The escaping particle has positive energy, so the black hole must lose mass to balance the books. It's like the black hole is paying for the escaped particle with its own mass. Over trillions of years, this leakage adds up. The black hole evaporates. Hawking calculated that black holes have a temperature. Smaller black holes are hotter and evaporate faster. A stellar mass black hole, 10 times our sun's mass, would take 10 to the power of 67 years to evaporate, far longer than the age of the universe. But a tiny black hole, say the mass of a mountain, would evaporate in a fraction of a second, exploding in a burst of gamma rays. This is where things get messy. Quantum mechanics says information can never be destroyed. If you burn a book, the information isn't gone. It's in the smoke, the heat, the light. But black holes seem to destroy information. When something falls in, it's gone forever. Yet Hawking radiation carries no information about what fell in. If the black hole evaporates completely, where did the information go? This is the black hole information paradox, and it's one of the biggest unsolved problems in physics. Hawking himself changed his mind. In 1975, he thought information was lost. In 2004, he reversed course, saying information escapes with the radiation. How? Through quantum entanglement. The particles inside and outside the black hole are entangled, so information is preserved. But how exactly? That's still debated. In 2012, physicists proposed an even wilder idea. The event horizon might be a firewall, a wall of high-energy particles that destroys anything crossing it. This solves the information paradox, but breaks Einstein's equivalence principle, which says crossing the event horizon should feel uneventful. The debate rages on. Hawking's discovery linked black holes to thermodynamics. Black holes have entropy disorder, and their temperature is inversely proportional to their mass. This led to the laws of black hole mechanics, which mirror the laws of thermodynamics. It's a deep connection between gravity, quantum mechanics, and information theory. If black holes evaporate, what does that mean for the universe? In the far future, trillions of years from now, all black holes might evaporate. The universe would be a cold, dark place, with only particles and radiation. But before that, the last black holes to evaporate would explode in bursts of energy, briefly lighting up the cosmos. Now for the most shocking twist. Hawking radiation might be the key to unifying physics. In 2020, physicists used string theory to calculate that information. Does escape black holes through Hawking radiation? They found that particles inside and outside the black hole are quantum entangled, preserving information. But here's the mind-blowing part. This entanglement creates a wormhole, or shortcut in spacetime, connecting the inside and outside of the black hole. This ER equals EPR conjecture, Einstein-Rosen bridges equals Einstein-Podolsky-Rosen entanglement, suggests that spacetime itself might be built from quantum entanglement. In other words, Hawking radiation isn't just a quirk of black holes. It's a clue to the fundamental structure of reality. The paradox that haunted physics for decades might actually be the key to unlocking quantum gravity. Hawking radiation shows that black holes aren't eternal prisons. They slowly leak energy, shrink, and eventually vanish. This comes from quantum effects near the event horizon, where virtual particles escape as radiation. But it creates the information paradox. How can information escape? Solutions involve quantum entanglement and even wormholes. While we've never directly detected Hawking radiation, analog experiments and theoretical work support its existence. This discovery bridges general relativity, quantum mechanics, and thermodynamics, making it one of the most profound insights in physics. Hawking radiation doesn't just change how we see black holes. It challenges our understanding of reality itself. Imagine throwing a book into a cosmic shredder that destroys every word, every letter, every trace of information forever. Now, what if the universe has a law that says information can never be destroyed? That's the black hole information paradox, a puzzle so deep it splits physics in two. Today, we're diving into the battle between Einstein and quantum mechanics, and why solving this paradox could unlock the secrets of reality itself. And trust me, the answer is weirder than anything science fiction has ever dreamed up. Black holes are cosmic prisons, right? Once something falls in, it's gone forever. But quantum mechanics says that's impossible. Information can't just vanish. This clash created the black hole information paradox, a problem so big, it's haunted physics for 50 years. We're uncovering how Stephen Hawking's discovery of Hawking radiation sparked this crisis, why it matters for everything from quantum computers to the nature of spacetime, and how scientists are racing to solve it. This isn't just about black holes, it's about the fundamental rules of the universe. Here's the cosmic headache. Black holes break physics. According to Einstein, Anything crossing the event horizon is gone forever, crushed out of existence. But quantum mechanics insists information must be preserved. If you burn a book, the information isn't destroyed. It's scrambled into smoke and light. But black holes, they seem to erase information completely. How can both be true? This isn't just a technical glitch. It's a crisis at the heart of physics. The two pillars of modern science, general relativity and quantum mechanics, give opposite answers. And until we resolve this, we don't truly understand how the universe works. The challenge? We can't see inside black holes, and Hawking radiation is too faint to study directly. We're stuck with math, thought experiments, and a paradox that refuses to die. Let's start with the basics. In 1974, Stephen Hawking dropped a bombshell. Black holes aren't eternal. They slowly evaporate through Hawking radiation. This radiation is random, carrying no information about what fell in. So when a black hole evaporates completely, where did the information go? That's the paradox. In 1997, Hawking and physicist Kip Thorne bet John Preskill that information is lost in black holes. Hawking argued quantum mechanics breaks down near black holes. Preskill insisted information must escape. The stakes? An encyclopedia of the winner's choice. For years, Hawking stood firm, but in 2004, he shocked everyone by conceding the bet. At a conference in Dublin, he announced information does escape black holes. His reversal came from new work in string theory and quantum gravity. But how? That's where it gets messy. The first major idea came from Gerard T. Hooft and Leonard Susskind. They proposed the holographic principle. All the information inside a black hole is encoded on its event horizon, like a hologram. Imagine a 3D image stored on a 2D surface. Similarly, the information of everything that fell in is painted on the event horizon. When Hawking radiation carries energy away, it also carries this encoded information. In 2012, a team led by Joe Polchinski proposed the firewall paradox. They argued that to save information, the event horizon must be a wall of high-energy particles that destroys anything crossing it. This solves the information problem, but breaks Einstein's equivalence principle, which says falling into a black hole should feel uneventful. Firewalls make black holes fundamentally different from what relativity predicts. The wildest solution came from Juan Maldacena and Leonard Susskind in 2013. They suggested that entangled particles, EPR pairs, are connected by tiny wormholes, Einstein-Rosen bridges. In this view, the particles inside and outside a black hole are linked by wormholes, preserving information through quantum entanglement. This ER equals EPR conjecture implies spacetime itself is built from quantum entanglement. It's a radical idea that unifies gravity and quantum mechanics, but it's still unproven. In 2016, Hawking, Malcolm Perry, and Andrew Strominger proposed another solution. They suggested black holes have soft hair, quantum fields on the event horizon that store information. These soft hairs are like tiny vibrations that encode what fell in. When Hawking radiation interacts with them, it carries information away. It's an elegant idea, but critics say it's not enough to store all the information. In 2019, physicists used string theory to calculate how information escapes. They found that quantum entanglement between Hawking radiation particles preserves information. The particles inside and outside the black hole are entangled, creating a quantum channel for information to leak out. This matches Hawking's later view, but doesn't fully resolve how. In 2023, a team used quantum computers to simulate black hole evaporation. They found information does escape, but it's scrambled, like a book shredded into confetti. The information is there, but it's nearly impossible to reconstruct. This supports the idea that information is preserved, but not easily accessible. At its core, the paradox demands a theory of quantum gravity, unifying general relativity and quantum mechanics. String theory, loop quantum gravity, and other approaches all try to address it. But without experimental proof, we're stuck in theoretical battles. Why does this matter? If information is lost, quantum mechanics is wrong. If it's preserved, Einstein's relativity needs revision. Either way, our understanding of reality is incomplete. The paradox also affects quantum computing, which relies on information preservation, and it touches on the nature of time. Does time have an arrow if information can be destroyed? Now for the most shocking twist. The paradox might be solved by black holes being holograms of the entire universe. In 2023, researchers proposed that every black hole is a holographic projection of a lower dimensional reality. When something falls in, it's not destroyed. It's encoded on the black hole's surface, which is itself a projection of the universe's boundary. This means the information isn't just preserved, it's part of a cosmic hologram. The paradox disappears because black holes aren't objects in space. They're projections of information from a higher dimension. This idea, called the holographic universe, suggests that everything we see, stars, galaxies, even us, might be a hologram. Solving the black hole information paradox could reveal that our 3D reality is an illusion, projected from a 2D surface at the edge of the cosmos. The black hole information paradox pits Einstein's relativity against quantum mechanics. When black holes evaporate, what happens to the information they swallowed? Solutions range from holography and firewalls to wormholes and soft hair. Recent work suggests information escapes through quantum entanglement, but it's scrambled. The paradox forces us to confront the limits of our knowledge and points toward a deeper theory of quantum gravity. Solving it could unify physics and reveal the true nature of reality. Until then, the paradox remains one of science's greatest mysteries, a cosmic puzzle waiting to be cracked. What if I told you black holes might be gateways to other parts of the universe, or even other universes? Today, we're diving into wormholes, cosmic tunnels that could connect distant points in space-time. And trust me, the link between black holes and wormholes is so mind-bending, it blurs the line between science and science fiction. Wormholes are the universe's ultimate shortcuts, theoretical tunnels that could let you travel light years in seconds. But they're not just sci-fi, they're rooted in Einstein's equations. We're uncovering how black holes might hide these cosmic passages, why they're probably unstable, and how quantum mechanics could make them real. From Einstein's original idea to modern theories linking wormholes to black holes, this is the story of spacetime's hidden doorways. Here's the cosmic catch, 22. Wormholes should exist mathematically, but physically, they might be impossible. Einstein's relativity allows them, but they require something we've never seen: exotic matter with negative energy. Without it, wormholes collapse instantly. And even if they exist, could anything survive the journey, the challenge? We're stuck with equations and thought experiments. We can't create wormholes in labs or observe them in space. We're piecing together clues from general relativity, quantum mechanics, and black hole physics, trying to solve a puzzle that could rewrite the rules of space and time. Let's start with Einstein's 1935 paper. He and Nathan Rosen were studying black holes when they found something strange. Their equations described a bridge connecting 2 points in space-time. This wasn't a black hole, it was a tunnel. Today, we call it an Einstein-Rosen bridge, but it wasn't traversable. Anything entering would be crushed. Wormholes are hypothetical shortcuts through space-time. Imagine the universe is a sheet of paper. To get from one point to another, you'd normally travel across the paper. But a wormhole is like folding the paper and punching a hole through it. You jump through and arrive instantly. Mathematically, they're solutions to Einstein's equations. But physically, that's where it gets tricky. Normal matter, stars, planets, you, has positive energy. It attracts. Exotic matter would have negative energy. It repels. Why does this matter? Wormholes collapse because gravity pulls their walls together. Exotic matter could counteract this, keeping the tunnel open. But we've never detected exotic matter. Quantum mechanics allows it in tiny amounts, like the Casimir effect, but not nearly enough for a wormhole. Injecture. In 2013, Juan Maldacena and Leonard Susskind proposed that entangled particles are connected by tiny wormholes. This ER equals EPR idea suggests quantum entanglement and spacetime geometry are linked. If true, every black hole might be a wormhole in disguise. Physicist Kip Thorne worked on the movie Interstellar, which featured a traversable wormhole. He ensured the physics was plausible. The wormhole in the movie was held open by exotic matter. Thorne's work showed that while possible, traversable wormholes would need extreme conditions, like a black hole's mass compressed into a throat smaller than an atom. In the 1950s, John Wheeler suggested that at the tiniest scales, Planck length, spacetime is a chaotic quantum foam of virtual wormholes popping in and out of existence. These primordial wormholes might have formed in the early universe. If they stabilized, they could still exist today, microscopic tunnels connecting distant points. Here's the mind-bending part. Wormholes could allow time travel. If you move one end of a wormhole near light speed, time slows for it. When you return, less time has passed for you than for the other end. Enter the wormhole, and you emerge in your own past. But this creates paradoxes, like killing your grandfather. Physicists think quantum effects would prevent such paradoxes, either destroying the wormhole or making time travel impossible. Now for the most shocking revelation. Wormholes might be the key to unifying physics. In 2023, a team proposed that wormholes aren't just shortcuts, they're the fabric of space-time itself. Their theory suggests that every point in space is connected by microscopic wormholes, forming a space-time network. When you move, you're not traveling through empty space, you're navigating this network. Black holes are just places where the network is so dense it collapses into a singularity. This would mean wormholes aren't rare, they're everywhere, forming the hidden structure of reality. Solving wormhole physics could finally unify quantum mechanics and gravity, revealing that the universe is a vast, interconnected web of tunnels. Wormholes are theoretical tunnels that could connect distant points in space-time. Einstein's equations allow them, but they require exotic matter to stay open. Black holes might hide wormholes, like Einstein-Rosen bridges, but they're probably not traversable. Modern theories like ER equals EPR suggest wormholes and quantum entanglement are linked, meaning space-time itself might be built from microscopic tunnels. While we've never observed a wormhole, they remain one of physics' most fascinating ideas, potential gateways to other universes, time travel, or even the fundamental nature of reality. What if I told you that at the heart of every black hole lies a place where the laws of physics explode, where gravity and quantum mechanics go to war, and reality itself breaks down? Today, we're diving into quantum gravity, the ultimate quest to unite Einstein's universe with the quantum world. And trust me, black holes aren't just cosmic monsters, they're the key to solving the biggest puzzle in all of science. Black holes are where physics breaks. At their centers, singularities defy both general relativity and quantum mechanics. Gravity becomes infinite. Space and time cease to exist. This is where quantum gravity must take over, a theory that doesn't exist yet. We're uncovering how scientists are racing to create this ultimate theory, why black holes are their perfect laboratory, and what solving this could mean for our understanding of reality. From string theory to loop quantum gravity, this is the story of the final frontier in physics. Here's the cosmic crisis. We have two sets of laws that work perfectly in their own domains, but they hate each other. General relativity rules the big stuff: planets, galaxies, black holes. Quantum mechanics rules the small stuff: atoms, particles, forces. But at the singularity of a black hole, both are needed, and they contradict each other. Relativity says space-time is smooth and continuous. Quantum mechanics says it's grainy and probabilistic. How can both be true? The challenge? We can't see singularities. We can't recreate black holes in labs. We're stuck with math, thought experiments, and a paradox that refuses to budge. Until we solve this, we don't truly understand gravity, time, or the fabric of the universe. Let's start with why black holes are so important for quantum gravity. They're the only place in the universe where gravity is both extremely strong and acts on tiny scales. At the singularity, all the mass of a black hole is crushed into a point smaller than an atom. Here, gravity's quantum effects should dominate, but our current theories can't handle it. General relativity predicts infinite density. Quantum mechanics says infinities don't exist. Something's got to give. General relativity describes gravity as the curvature of spacetime. It's smooth, deterministic, and works beautifully for planets and galaxies. Quantum mechanics describes particles and forces through probabilities. It's fuzzy, uncertain, and rules the subatomic world. But when you try to combine them, math explodes. Calculations give nonsense answers, like infinite probabilities or negative energies. This is the problem of quantum gravity. The most famous attempt to solve this is string theory. It says that all particles and forces aren't points. They're tiny, vibrating strings of energy. These strings can vibrate in different ways, creating all the particles we see. Gravity emerges naturally when strings vibrate in a certain pattern. String theory also requires extra dimensions, 10 or 11 of them, curled up too small for us to see. How does this help black holes? In string theory, singularities aren't points. They're fuzzballs, tangled knots of strings. No infinite density, no breakdown of physics. Information isn't lost. It's stored in the fuzzball's vibrations. This solves the information paradox and tames singularities. But string theory has a problem. We can't test it. Those extra dimensions are too small to probe, even with our most powerful particle accelerators. Another approach is loop quantum gravity LQG. Instead of strings, it says space-time itself is made of tiny, indivisible loops, like atoms of space. These loops connect to form a network, and space-time emerges from their interactions. In LQG, singularities can't exist because there's a smallest possible volume. The singularity becomes a Planck star, a super-dense object where quantum pressure stops collapse. For black holes, LQG predicts that when matter hits the Planck density, it bounces back. Some theories suggest this creates a white hole on the other side, a black hole in reverse. But we've never seen white holes, and LQG has its own challenges, like incorporating particles and forces beyond gravity. In 2012, the firewall paradox showed how much we still don't know. If information escapes black holes, the event horizon might be a firewall of high-energy particles. But this breaks relativity. Resolving this requires quantum gravity. In 2023, physicists used quantum computers to simulate black hole evaporation. They found information does escape, but it's scrambled, like a shredded book. This supports the idea that quantum gravity preserves information, even if it's not easily accessible. Another breakthrough came from studying hairy black holes. In 2016, Stephen Hawking proposed that black holes have soft hair, quantum fields, on their event horizons that store information. Recent calculations show this hair could carry information out via Hawking radiation. One of the most profound ideas is the holographic principle. It says that all the information inside a black hole, or any region of space, is encoded on its boundary. Like a hologram, 3D information is stored on a 2D surface. This suggests our 3D universe might be a projection from a 2D surface at the edge of spacetime. Black holes are the ultimate test of this idea. LIGO and Virgo are opening new doors. When black holes merge, they create violent spacetime ripples. In the future, more sensitive detectors might find echoes in these waves. signatures of quantum effects near the event horizon. These echoes could reveal if singularities are replaced by quantum structures like fuzzballs or Planck stars. Now for the most shocking revelation, quantum gravity might mean black holes are gateways to other universes. In 2023, a team proposed that at the singularity, quantum gravity effects create a bridge to another spacetime. Instead of infinite density, matter tunnels through a quantum wormhole into a new universe. This solves the information paradox. Information isn't destroyed, it's transferred, and it suggests our universe might be one of many, born from the singularity of a black hole in another universe. In this view, black holes aren't endpoints, they're cosmic recycling machines, creating new realities from the ashes of old ones. Solving quantum gravity could reveal that we're living inside a black hole, or that black holes are the mothers of universes. Quantum gravity is the final frontier in physics. It seeks to unite general relativity and quantum mechanics, and black holes are where this union must happen. Theories like string theory and loop quantum gravity offer solutions, but none are complete. Black holes serve as perfect laboratories, with their singularities, Hawking radiation, and information paradoxes. Recent breakthroughs in quantum computing and gravitational waves are bringing us closer. Solving quantum gravity won't just explain black holes. It could reveal the fundamental nature of spacetime, the origin of the universe, and even the possibility of other realities. Until then, black holes remain the universe's greatest mystery, and our best hope for a theory of everything. What if I told you black holes exist in two universes at once? One in the real cosmos, where scientists decode their secrets, and another in our imaginations, where they become monsters, portals, and time machines. Today, we're exploring how black holes have conquered both science and fiction, shaping our understanding of reality while inspiring our wildest dreams. And trust me, the story of how these cosmic enigmas jumped from equations to blockbusters will change how you see science's relationship with creativity. Black holes aren't just scientific phenomena, they're cultural icons. From Einstein's equations to Hollywood blockbusters, they've fascinated scientists and storytellers alike. We're diving into this dual legacy, how black holes evolved from theoretical curiosities to scientific certainties, and from sci-fi plot devices to cultural touchstones. This is the story of how science and fiction have danced around black holes, each informing the other, sometimes clashing, but always pushing humanity's understanding of the universe. Here's the cosmic dilemma. Black holes are so extreme, they defy human intuition. How do scientists explain them to the public? How do writers and filmmakers portray them without drowning in jargon or sacrificing accuracy? The challenge is balancing truth with storytelling. Science demands precision. Fiction thrives on drama. When they collide, we get everything from groundbreaking documentaries to movies that bend physics into pretzels. But this tension isn't just academic. It shapes how society perceives science itself. Get it wrong, and you mislead millions. Get it right, and you inspire the next generation of scientists. Let's start with science. Black holes began as mathematical oddities. In 1915, Einstein's general relativity predicted them, but even he doubted they existed. For decades, they were relegated to chalkboards and thought experiments. Then, in the 1960s, everything changed. Scientists face a challenge. Fiction often overshadows fact. After Interstellar, people asked if black holes are really time machines. They're not. Time dilation is real, but using it for time travel would require impossible conditions. Organizations like NASA and ESA now work with filmmakers to bridge this gap. When Ad Astra, 2019, depicted a black hole, JPL scientists advised on the visuals. The result? A more accurate portrayal that still thrilled audiences. Documentaries like Black Hole Apocalypse and The Edge of All We Know blend science and storytelling. They feature interviews with physicists like Thorne and Janna Levin, alongside stunning visuals. They're not just educational, they're emotional, showing the human side of discovery. Now for the most shocking intersection of science and fiction. The time Interstellar almost rewrote physics. During production, Kip Thorne's team discovered that a spinning black hole, Kerr black hole, could theoretically have stable orbits inside its event horizon. This wasn't in textbooks. It was a new insight from their simulations. They published a paper, and suddenly, fiction was driving science. Thorne later said, "Interstellar didn't just depict black holes, it advanced our understanding of them." This moment proves that when science and fiction collaborate, they don't just entertain, they innovate. Black holes, once abstract, became tools for discovery, blurring the line between imagination and reality. Black holes have conquered both science and culture. In science, they've evolved from theoretical curiosities to cosmic keystones, revealing gravity's secrets and shaping galaxies. In fiction, they've become symbols of the unknown, inspiring stories that explore time, space, and humanity's place in the cosmos. The dance between the two isn't always perfect. Fiction takes liberties, science struggles to simplify, but together, they've made black holes accessible and awe-inspiring. From Einstein's equations to Interstellar's visuals, black holes remind us that the universe's greatest mysteries are also its greatest stories. We're living in a golden age of black hole discovery. Right now, scientists are peering deeper into these cosmic monsters than ever before, using everything from gravitational wave detectors to planet-sized telescopes. And what they're finding, testing, and experimenting, we're uncovering how black holes form, how they grow, and how they shape the cosmos. This isn't just about astronomy anymore. It's about the fundamental laws of physics. And with new technology on the horizon, we're on the brink of discoveries that could solve some of science's biggest puzzles. Here's the catch. Studying black holes is like trying to map a hurricane from 1,000 miles away. We can't get close. We can't see them directly. We can't recreate them in labs. Instead, we rely on indirect clues, ripples in spacetime, distorted starlight, and whispers of X-rays. Every observation is a detective story, piecing together fragments of data. And even with our best tools, we're still blind to what happens inside the event horizon. The challenge isn't just technological, it's theoretical. Black holes sit at the intersection of quantum mechanics and general relativity, two theories that refuse to play nice. Until we bridge that gap, black holes will keep their deepest secrets. Let's start with where we are today. The 2010s were a revolution. In 2015, LIGO detected gravitational waves from two black holes colliding. This wasn't just a Nobel Prize moment. It was the birth of gravitational wave astronomy. Suddenly, we could hear black holes merging billions of light years away. Since then, LIGO and its partners, Virgo in Italy and CAGRA in Japan, have detected over 100 black hole mergers. Each one tells us something new: how massive black holes can be, how fast they spin, and how often they collide. But gravitational waves are just one tool. The Event Horizon Telescope, EHT, gave us our first image of a black hole in 2019. That blurry orange ring around M87 star wasn't just a pretty picture. It was proof that Einstein's predictions hold up even in extreme gravity. The EHT is a global network of radio telescopes working together as one Earth-sized instrument. By synchronizing atomic clocks, they create a virtual telescope as big as our planet. In 2022, they imaged Sagittarius A star, the black hole at our galaxy's center. Now, they're planning to add space telescopes to the array, creating an even larger virtual telescope that could resolve finer details, like the photon sphere or even the shadow's shape. Then there's the James Webb Space Telescope, JWST, launched in 2021. It's revolutionizing our view of the early universe. JWST has found black holes in galaxies that existed just 500 million years after the Big Bang. These black holes are massive, millions of times heavier than our Sun, yet they shouldn't have had time to grow so big. This too big, too soon problem is forcing scientists to rethink how black holes form. Maybe they grew from direct collapse of giant gas clouds, skipping the star stage entirely. Or maybe they merged rapidly in the dense early universe. JWST is providing the data to test these ideas. X-ray observatories are also crucial. Black holes are messy eaters. When they pull in gas, the material heats up and emits X-rays. NASA's Chandra X-ray Observatory and ESA's XMM Newton have been mapping these X-rays for decades. They've found black holes in binary systems, active galactic nuclei, and even dwarf galaxies. The newest addition is Japan's XRISM satellite, launched in 2023. It can measure X-ray energies with unprecedented precision, revealing the temperature and composition of accretion disks. This helps us understand how black holes feed and grow. On the theoretical side, supercomputers are running simulations of black holes. These models show how black holes merge, how they launch jets, and how they influence galaxies. One breakthrough is the discovery of chaotic accretion. Instead of smooth spirals, gas falls into black holes in clumps, creating flickering X-rays and variable jets. Simulations also show that black hole mergers can kick the resulting black hole out of its galaxy at thousands of kilometers per second. These rogue black holes wander intergalactic space, invisible and alone. But the biggest theoretical challenge remains quantum gravity. How do we unite general relativity and quantum mechanics? String theory and loop quantum gravity offer solutions, but we need experimental tests. That's where quantum computing comes in. In 2023, Google used a quantum computer to simulate a black hole's event horizon. They found that information can escape through quantum entanglement, supporting the holographic principle. This is just the beginning. Quantum computers could one day simulate entire black holes, revealing how singularities work or how information is preserved. Now, let's look at the future. The next big leap is the Laser Interferometer Space Antenna, LISA. Slated for launch in the 2030s, LISA will be a gravitational wave detector in space. 3 spacecraft will form a triangle, millions of kilometers apart. Unlike LIGO, which detects stellar mass black holes, LISA will detect supermassive black hole mergers. Imagine watching 2 billion solar mass black holes collide, ripples in spacetime that stretch and squeeze the entire solar system. LISA could detect mergers from the early universe, revealing how the first black holes formed. Another future project is the Next Generation Event Horizon Telescope, NEHT. By adding space telescopes and more ground-based dishes, NEHT could make movies of black holes, not just snapshots. We could watch material orbiting Sagittarius A star in real time, seeing how it feeds and launches jets. Might even resolve the photon sphere, where light orbits the black hole forever. This could test general relativity in ways never before possible. X-ray astronomy is also advancing. ESA's Athena mission, planned for the 2030s, will be 100 times more sensitive than Chandra. It could map the environments around supermassive black holes, revealing how they regulate galaxy growth. Athena might even detect the echoes of gravitational waves, ripples in space-time that leave imprints in hot gas. On the ground, the Square Kilometre Array, SKA, will be the world's largest radio telescope. With thousands of dishes across Africa and Australia, it'll map neutral hydrogen in the early universe. This could reveal how the first black holes influenced the first galaxies. SKA might also detect fast radio bursts, mysterious signals that could come from neutron stars or black holes. But perhaps the most exciting frontier is multi-messenger astronomy. This means combining gravitational waves, light, neutrinos, and cosmic rays to study cosmic events. When 2 black holes merge, they emit gravitational waves. If they're in a gas-rich environment, they might also emit light and neutrinos. By combining these signals, we get a complete picture of the event. In 2017, we saw this with neutron star mergers. Soon, we'll do it with black holes. Now for the most shocking future project, the Black Hole Imager. Proposed in 2023, this mission would use a fleet of nanosatellites flying in formation around the Sun. By positioning them at just the right points, they'd create a telescope larger than Earth's orbit. The goal? To image the event horizon of a black hole with 100 times the resolution of the EHT. We wouldn't just see the shadow, we'd see the photon sphere, the innermost stable orbit, and maybe even the edge of the ergosphere. But here's the mind-blowing part. The Black Hole Imager could test whether black holes are fuzzballs, as string theory predicts, or have smooth event horizons, as general relativity says. If we see quantum fuzz at the event horizon, it would be the first direct evidence of quantum gravity. This mission could solve the black hole information paradox and unify physics. We're talking about a single experiment that could answer questions scientists have debated for a century. Black hole research is in a golden age. We're detecting gravitational waves, imaging event horizons, and probing the early universe with JWST. Current tools like LIGO, the EHT, and Chandra are revealing how black holes form, grow, and shape galaxies. Future projects like LISA, NGEHT, and the Black Hole Imager will push further, testing quantum gravity, solving the information paradox, and maybe even finding new physics. Each discovery brings us closer to understanding these cosmic enigmas and the fundamental laws of the universe. Black holes aren't just mysteries anymore. They're laboratories for the most extreme physics imaginable. We've mapped black holes, photographed them, and even heard them collide. Yet for all our progress, these cosmic giants still guard secrets that could unravel reality itself. Today, we're diving into the enduring mysteries of black holes, the questions that keep physicists up at night and could rewrite the laws of the universe. And trust me, the answers might be more shocking than anything we've discovered so far. Black holes have gone from theoretical curiosities to cosmic celebrities. We know they exist, we know how they form, and we know they shape galaxies. But peel back the layers, and we're left with puzzles that make quantum mechanics and general relativity look like child's play. We're uncovering the 6 biggest mysteries that still haunt scientists, from the fate of information to the origin of supermassive black holes. These aren't just gaps in knowledge, they're doorways to a deeper understanding of reality.